I came in here because I just checked and there's like 20 something people, and I'm like, oh, okay, there's a bunch of people who's in here. And then I saw
People are
Tapioca
bored.
Weasel and zzpop, and someone told me I should talk to zzpop about ether, I
Jesucristo.
guess.
ZZ Pop is the no ether master. He was the one who was telling me about.
Yeah, and apparently there's been a lot of interest in it. But I posted a video that hopefully would be very explanatory of the concept for anyone who's interested.
So, zzpop.
I'm not interested.
That's okay.
My question
watch it
is,
together.
Post it here.
my question
You
is
can watch
where
it
do
in your own
you
time.
where do you stand on your philosophical framework as it applies to physics? Like I believe I believe in scientific realism. Like that's my paradigm through which I view like physics.
What does that
God,
mean to you?
it's like a fucking snooze fest in here.
Well,
Yeah, I'm excited.
How is that a snooze fest? That's a fucking amazing topic.
Yeah, that was like a setup topic for them to continue talking about.
Yeah. So scientific realism, I mean, I guess you could say it means different things to different people, but the way I understand it, right, is like we live in a mechanical universe in which all interactions that take place are physically real. The reality we observe exists independently of our observation thereof. So like when we talk about, how if things interact, whether it be through direct kinetic action or thermal energy or electromagnetic interactions via fields, all those things are still at their core intrinsically physical and can be thought of mechanically. Even if it's not mechanically in the sense of like I'm pushing on something with my hand, there is still a physical, in some way, corporeal manifestation of those things. And it kind of flies in the face of the current paradigm where the Copenhagen theory is like the best way that they explain, QFT, in which things are not treated as all physically real. They use abstractions and things that are observer dependent in order to, say that there is like almost as if there's like a parallel layer of reality that's not physically manifest. And I just think that that's garbage. And the reason that we have things like gravity and electromagnetism is because there is some, substance, for lack of a better term, of mutual contact amongst all these bodies that allows there to be a mutual influence upon them.
Yeah, I don't like the Copenhagen interpretation at all. I feel like it's a cop out. I mean, it's basically, to me, it's a position of sort of agnosticism on what the equations of physics are talking about. It's an attempt to separate out the physical theories and the process of doing measurements from the what is being measured. And yeah, no, I don't like that. I think that's very philosophically confusing
Bankrupt.
and
It's about
cowardly.
the Copenhagen interpretation is bullshit. Okay, like it's not a real interpretation. It is a thing that you use in order to like shortcut to the point that you're trying to make about Bourne's rule.
It draws an arbitrary line between like the things under observation and the observer, the quantum world and the classical world that's observing it. And there's no basis in any part of reality for this kind of delineation. Yeah, so I'm not a
not
Copenhagener.
arbitrarily. You can make the delineation, but you can make it soundly. You can make it on the basis of actual sensible theories of decoherence.
Yeah. So I agree, Tapioca. I think it's a cop out, or I think it's garbage too. And I agree with zzpop. I think it's a cop out. Ultimately, if we just look at what happened in like a short 30 to 40 years, not even 40, yeah, like 30 years after Einstein dropped his theory. Mm-hmm. In the 20s, electrodynamics advanced a lot further, and it kind of advanced past the ability of Einstein's original a theory to be physically satisfactory in explaining measurements. And that's what kind of one of the reasons Einstein in the early 20s like kind of reneged on the idea that there's not an ether. He's like, oh, there would be an ether. He's just like, it just has to, not have the property of being able to measure motion relative to it. But everything else about it that we've always believed in would have to be true, because otherwise all this stuff would be meaningless. Like he essentially just treated space time as ether minus relative motion measurement.
Yeah,
Yeah.
I think that's fair, and I think that the minus the relative motion aspect is an extremely important part. It's not the same thing. Like Einstein believed in locality, and you can manhandle an ether theory if you just focus on locality into seeming to also be on the same page. It's not. Einstein had a very particular idea of what locality meant and causality and things like that. And those are not satisfied by ether theories. They're simply not.
Well, there's a big straw man that's usually applied. Like people act as if there was only one ether theory, and like there was never a settled agreement upon what it was, because they were trying to figure it out. But every time you read about it historically, people always try to pigeonhole it into this like stationary ether in the universe that the Earth's moving through, and there's no, they treated it as just like a fixed grid that didn't have any dynamicism to it. And
you always have to qualify it. You always have to qualify it and be like, I'm talking about a family of theories that respects this particular qualifier. And that can sometimes be a fairly general qualifier that you can rule out categorically. Like that.
But what's important to remember is like Einstein literally just took what already existed in terms of like Lorentz and Voigt. He took an ether theory with the fluid dynamics math involved, copied all of it, and just said this is no longer applied to a medium. This is applied to empty space-time absent of a medium, and he kept the math that described a physical relation that allowed for a physical interaction to take place, and removed the mechanism by which a physical action could happen, because the math had to be copied because it would accurately describe what happened. We get to the 20s and you get to Schrodinger.
You always have to do that.
Schrodinger solved the problem, basically. He figured out that everything is waves. And I mean, we already had De Broglie, and he kind of figured that out too, but Schrodinger took it past that and figured out how to describe things to their, nth degree via waves. And they didn't.
Sorry. I thought you were done.
No, almost finished. And so when Schrodinger solved that and made his wave equation and accurately described the hydrogen atoms emissions, he in the line spectra rather, they didn't like that, because what it implied is, oh wow, like he is describing something that is a continuous distribution of energy spread across space, a literal wave, physical wave in space. And we can't account for that in our theory because we've already agreed to not think of a medium. And so then Born makes his rule, and then Copenhagen, attaches onto it, and they treated everything as the probability of discrete point-like events taking place. When in reality, the very point-like nature of things is a product of A, the measurement problem, and B, the scale problem in time, the time scaling problem of measurement in relation to a moving wave. And so
I don't know exactly what you mean by that.
So when we talk about point particles, they literally had to create infinities and renormalization, because you can't have a particle that has mass that's a point. It creates infinite density, which obviously is made up. So in order to deal with the zeros and the infinities that are created by that, they had to invent data renormalization techniques, which are not a legitimate analytical solution. They are simply processing it into a usable form. And when you renormalize the data properly through enough renditions, you can get to an approximation that's pretty much the exact answer without just about the exact answer, to X many decimal points without having infinities. But they're artificially removed, right? Renormalization was never meant to be a real fix.
I've gone through these calculations in detail. They are shockingly intuitive when you follow them step by step.
Which calculations? Are you talking about Schrodinger's wave stuff, or are you talking about
the renormalization ones?
You're talking about like a Dyson series or what? Like which technique? There's multiple techniques we could do.
There are several layers of this. Okay, so you have renormalizable field theories, and the word renormalizable in a certain context means that they converge under a certain type of series. However, you have higher order series that don't converge under that series, but still have a very particular and predictable behavior. So you're still able to use them in a robust way that cancels out. And it's not magic. It really isn't magic.
Sounds like something a magician would say.
That's fair. That's legitimate. That's a legitimate response. I have no response to that particular criticism.
So like when he created renormalization in the first place, like it wasn't satisfying anybody. It wasn't meant to be a permanent fix, right? It was
not.
It was temporary because
it was also created. I apologize for cutting you off, but it was also created when normalization and renormalization were invented and discovered. They were before you had people in the 70s who really approached them from a much more mathematically and physically rigorous point of view.
Yeah, but if you think about what it actually did. Oh, sorry, Alan.
I was going to say real quick, none of them give physically meaningful solutions. Dyson, I forget the guy's first. Freeman Dyson, he was brought in to come up with like one of the first convergence series that they could use to renormalize everything. He did the opposite, where he took the inverse system to see if his equations were physically meaningful, and what they ended up producing was a catastrophe in a vacuum, essentially, and it didn't have any physically meaningful insights into reality. And he concluded that what he was doing with the math was physically meaningless, and he ultimately abandoned quantum mechanics and walked away from it and went on to teach like regular like astronomy or something. And then there was hold on 1 second. Oh, 1 second, dog. There was Dirac too, who actually is the godfather of quantum mechanics. He also abandoned the math too and was questioning it, whether it was physically meaningful. And as he was ending his career, he was working on an ether theory to reintroduce, but he was making sure that it was a physically meaningless ether theory that had so that motion wouldn't be relative to it because special relativity.
So I have that quote, or this is so like Freeman Dyson, as you said, he abandoned the theory, and then he had a conversation with Enrico Fermi, which you guys know Fermi. Fermi basically told Dyson that because Dyson, I forget how many free variables Dyson used in his power
series.
There's
like 21 not 21. There's like 7 or 8 free parameters or something. Yeah. And he's like,
and so Fermi told him, he said that so basically he said, with an equation of 3 free variables, I can draw an elephant. With 4 free variables, I can make it wiggle its trunk. And he was telling him, in other words, that it was physically meaningless and could be used to make the data say anything you wanted it to. You just add enough free variables. And so Freeman Dyson, later in 2006, he's like super old at this point, he writes about QED And he says, as one of the inventors of QED, I remember that we thought of QED in 1949 as a temporary and jerry-built structure with mathematical inconsistencies and renormalized infinities swept under the rug. We did not expect it to last more than 10 years before some more solidly built theory would replace it. Now, 57 years have gone by, and that ramshackle structure still stands. He's literally invented it, bro, and that's what he said about it.
And a very interesting set of things. Einstein went through a lot of different interpretations and
That was
of his
direct.
work, and there was one point
That
where
was Dyson.
Einstein. I'm jumping back to something earlier that was talked
Oh,
about.
okay.
So Einstein, because we were talking earlier about Einstein coming back around on a version of the concept of ether towards the end of his career. And part of my understanding of that is that at one point he thought general relativity could make all motion equally relative, equally perspective dependent. But then he realized that there was a physical difference between inertial versus accelerating that couldn't be gotten rid of. So even if different frames of constant velocity were indistinguishable, the difference between constant velocity versus proper acceleration was a real physical difference. And I think, though, I don't 100% remember without rereading it, that was one of the things that made him kind of come back around to being more pro ether again towards the end of
That
his
was
career.
never a thing that he had to realize. That was always like the fundamental distinction that he was using.
Well, no, because he
breaker.
invented special relativity first, and then after Sagnac discovered the Sagnac effect, he came up with patches via general relativity that borrowed from what was the guy's equation? Paul Gerber's equation.
So to do like the perihelion shift stuff, that was all from Gerber. But to bring in the framework or whatever, that was done through absolute differential calculus.
I want
which
to
he had
comment
someone else do for him.
based on some of the
What's
stuff
that?
that was said earlier. Is that I definitely agree in being critical of the Copenhagen interpretation. I'm very critical of the idea that the quantum fields are just a mathematical description of the probabilities of our observation of fundamentally point-like particles. I definitely would bet against the existence of point-like particles and in favor of what's going on is that there is some real physically existing, always present fluid-like substance, and sort of the detection of a quote-unquote point-like particle is more of a illusion created of our measurement devices and the way they detect perturbations within the fundamental field, as they're called, or the fundamental kind of fluid-like substance. I think that things like the Casimir effect point very strongly to the idea that quote unquote empty space is not empty. It has meaningful material properties to it that can be detected. I could say a lot of other things on that. We covered lots of different things in this talk, but before we move too far from it, I just wanted to cycle back to some of the earlier things that were said.
Yo, Alan, do you know
Yo.
about this no aether theorem, Alan?
Yep.
And so supposedly they're saying that it's an empty space and everything is just an empty space, no aether. And because it's an empty, meaningless space, there's a bunch of symmetries and emptiness. And that's why everything is conserved, like energy, momentum. It's actually the nothingness of the emptiness that conserves momentum and angular velocity and all these things. These guys don't really know about it. Nobody really knows about it. So maybe you know about it, Alan.
If I could jump in, it's not really a statement on space.
Yeah, if you could jump in and answer my question, that'd be dope. But
hold on, let him go.
But no, I'm not familiar with the idea of like of conservation laws or whatever being facilitated by no ether or whatever. I never heard of that one. But I did want to talk about vacuum properties and physical. You know, if the vacuum's not empty, then what's inside of it, all motion has to be relative to it, and you would have to explain why the Earth doesn't have a 30 kilometer a second velocity component. So, like the whole purpose of removing the ether was that so that all motion isn't relative to it. That was one of the biggest things that Einstein did, because the Lorentz framework that Einstein derives, so-called from his paper, is the same framework that Lorentz used, and the framework that Lorentz used was the framework that Voigt came up with, and the Lorentz transformation is just the Voigt transformation. You could either multiply by the gamma factor all the coordinates, and it'll be the longitudinal form, or you could divide by it, and it'll be the transverse form. So the framework is completely the same, right? They were just interpreting the mechanics of it being applied to the wave. So like instead of the coordinate system and the apparatus contracting, the wave's frequency and wavelength changed. Like that's the contraction mechanism that they were looking at in terms of the light wave relative to the medium that they were using. So the mathematical framework is actually completely identical and not unique or independent to an etherless theory, number one. And number two, like I said, if you're saying that the vacuum properties are physically real and meaningful, then guess what, my dude, we're in a medium. And if we're in a medium, all motion is relative to that medium. If you're in a pool and you're moving through that pool, your motion is relative to the water. And so if the same situation is applying in a vacuum, if epsilon and mu are physically real properties that dictate the velocity of a wave moving through it, which would be an electromagnetic wave, then all motion is relative to that medium. There's no way around it. And to say that there is an ether, but then all motion isn't relative to it, is like saying, you're in an ocean, but sonar isn't relative to the
Water.
to the water. That's absolutely preposterous, and that needs reconciled. And that's something I wanted to talk to you about, zzpop, because I know you have an absolute frame Einstein theory, and I don't know if you ever heard of Solari, but Solari and a couple of other lads were trying to introduce the concept of an absolute frame in the Einstein framework, which is just the Lorentz framework, which already has an absolute frame
The
for all
Solari
motion
paradox.
relative to but they just never. But if you take that approach, then that begs the question: where's the motion of Earth relative? What's that one relative to? And it's not reconcilable. That's why they could never bring back a physically meaningful ether theory. That was the whole purpose of it. And that's why Einstein said, when he was talking about the general theory, when he was like, oh, maybe there is an ether, he made sure to make a special comment that, make sure you don't attribute physical properties to it, and treat it like an abstract fluid structure. He was like, if that helps you conceptualize space-time, that's great. But don't ever attribute it to anything physically real. Because if you and he didn't say this part, but the implication though would be if you did, all motion would be relative to it. So you can't have it both ways. Go ahead.
Yeah, I was just gonna say that I read that quote a second ago to all you guys. He's like, the one where he's like, if I have 4 free variables, I can draw an elephant, and 5 I can make it wiggle its trunk. It's 4 and 5, not 3 and 4. But right after that, because I don't know if you guys know the famous reply to that, because the reply was Feynman. Like Feynman had a response. His criticism, or Feynman's response to these criticisms, right, between Dyson and Fermi, was shut up and calculate. But a lot of people don't know that, not only did Freeman Dyson write that, but there was another crazy quote from Paul Dirac. So you've got Enrico Fermi, you've got Freeman Dyson, and you've got Dirac, all of them criticizing it. And these are the literal inventors. And Dirac said renormalization is just a stopgap procedure. There must be some fundamental change in our ideas, probably a change just as fundamental as the passage from Bohr's orbit theory to quantum mechanics. When you get a number turning out to be infinite, which ought to be finite, you should admit that there is something wrong with your equations and not hope that you can get a good theory just by doctoring up that number. So you've got all these guys. All of this piggybacks off of the problem of taking Schrodinger's wave equation, which relies upon a real physical wave in space. Schrodinger said that himself. He said he believed it represented, he invented it. He said it represented a real wave in space.
Doesn't mean it does.
And you take that and Okay, sure, but then you just run into the problems that
It's just a mathematical framework dependent on a wave and a medium, but it doesn't imply that.
Yeah, it just happens to be via
Yeah,
pure coincidence to describe reality that's not a wave. But
it works though. It works though. And it
anyway,
works
but
quite
it
well.
doesn't, which is why these three
It does work,
inventors,
which is why you have, which
these
is why
three
you're here. And I can
inventors
hear your
of
voice.
QED that I just
Do not
quoted
interrupt,
to you,
please. Thank you.
yeah, these three inventors of QED that I just quoted to you all criticized it, and they were all like, "Yeah, we didn't do this because we thought it actually made sense or was real. We were just trying to get the math to work to get an answer, and it was never meant to be permanent, and it sucks, and it doesn't mean anything." That's what they all said. The only one who was like, famous more than everybody else was Feynman. Why is he famous? He happens to be the one that said, "Shut up and calculate," because he didn't care. But
You
as
didn't
Alan
say that, man. That
Feynman didn't
wasn't
say, "Shut
him.
up and calculate."
That was
dude. Not only did he say that when he was asked about his Feynman, or what was it, the Feynman diagrams that he presented at the Soive meeting or conference that they had when they were putting together the Copenhagen interpretation. Everyone was very excited because he had this solution to this divergent series, and so people were like, "Hey, so how'd you come up with these solutions?" And he was like, "Oh, well, I don't really know, but it gives the correct answer, so that's all that's important."
That's different from shut up and calculate. That's not the same thing at all. One of those is hold on. One of those is the Ramanujan approach of just having an insight, and one of them.
Tappy, if I'm presenting a fucking formula where I'm like, "Hey, I just came up with this really cool solution. Here's how I derived it," and then you say, "Hey, how'd you derive that, by the way?" And I say, "Well, it doesn't matter, but it gives this correct solution." That's literally analogous to shut up and calculate. Number one, okay?
No.
Yeah. Oh yeah.
Oh
yeah. Check the chat. I gave you the link, Tapioca. Here's a paper with all the quotes in it and the references.
I don't think those are the same thing. I think those are questions that arise in completely different aspects of the entire scientific process. But fair enough.
Yeah.
What the heck? Dude, shut up and calculate, and then also, does it work? Okay, it works. Don't question it. It's the same exact thing as a dismissal.
It's like identical.
But back to the tying it back to Einstein, what everything Alan just explained, right? So post that shift from the Born rule to treat Schrodinger's wave equation as a bunch of point particle events and probability distribution of event occurrences, right? We entered a regime of physics in which things stopped obeying scientific realism, which is my premise in all of this. Like I view the world through the lens of scientific realism, because if you don't accept Schrodinger's wave equation as being descriptive of a wave in space, and you don't accept a medium, you don't accept physical properties of the universe, which are material properties, which every material has a material constant table, which it has to be material to have material properties, otherwise it would be immaterial not have them. If you take all these equations and accept them as describing reality, which you have to because they do, but you remove the physicality to them, you end up in this regime where everything's abstract, has no physical meaning. It somehow has energy and carries energy and momentum and interacts in physical space with matter and transfers and transmits energy and information, yet it's not physically real. It's literally virtual fields and virtual particles that pop in and out of our plane of existence in order to satisfy mathematical laws, which themselves are immaterial. That is retarded. If you believe that, God help you. We live in a physical world that is physically real and things physically happen. There is not an abstraction that exists only in the minds of people, which must be satisfied through virtual entities that don't physically exist that somehow manifest in our physical plane. You might as well just believe in freaking Hinduism at that point.
Yeah, I don't like this common description of virtual particles, and there's people who are pursuing approaches to quantum field theory where you do treat space as a very physically real dielectric medium. Dielectrics are things with positive and negative ends. So rather than saying, oh, virtual particles come into existence and annihilate back out of existence, You just interpret that as the energized oscillations of the dielectric material. The dielectric material, made of things with positive and negative ends. If they get energized, they can vibrate, they can stretch out further away from each other. And you're like, oh, here's a positive charge, here's a negative charge for a little bit. They didn't come into existence out of nowhere and disappear from existence. You're just flicking
That's what they say, though, bro.
elastic.
We completely agree upon that. But the physical interpretation has to be etherless, and there can't be a real dielectric medium that will ever be accepted because all motion has to be relative to it. So
right, you can't acknowledge it halfway, right? You can't your intuition and your knowledge of physical reality points you to say, well, obviously, we can treat superfluid vacuum theory does it. That's one of the more emergent recent theories in the past 10 to 20 years. It's really gained a lot of traction in the past 3 to 5 years. Check it out. Its Wikipedia page is interesting, but superfluid vacuum theory and other theories like that do try to treat space as a plenum filled with an ever-present field everywhere that is physically a superfluid or some other similar type of material. So it posits that space is filled with some type of either a superfluid or some other elastic solid with similar properties, maybe a Bose-Einstein condensate, for example, or something else that allows for the physical satisfaction and resolution of fluid dynamics in every energetic reaction in reality. That is what we're proposing. We're just telling you that it's the ether, because if you don't accept a real medium, then you can't have physical explanations for any of this stuff. And if you try to say, okay, there is a physical medium, then all of a sudden Einstein's theory cannot be valid. You can't have both. It's a catch-22. And that's our whole point that we're trying to tell people and explain it. You have to pick one or the other. One obviously has a bunch of glaring problems. The other one has zero problems whatsoever. The only problem that you could possibly say that it has is the inability to measure Earth's motion. That's it.
Yeah. And I think you mean catch-33, by the way. But anyway, continues easy.
I mean, I think I agree with everything up until the claim that if it's a real physical medium, therefore you would definitely be able to detect linear motion through it. I think that's a bit of a leap. It's because the thing is that we're not outside of the medium. It's not like watching a wave propagate through a medium when you're an outside observer to it. We're within it. We're made of it.
We are made of it.
Down to the atoms in our bodies.
Yeah, that doesn't change anything about it.
Well, it means
apply sonar scenario to it, bro. It's the same thing.
Sonar,
if you're in a medium, the motion's relative to it. Did you know GPS will it's a timing interval system, so it accurately derives your position based on your velocity relative to the ECI frame, which is just the center of Earth stationary fixed. So did you know GPS will it's a timing interval system, so it accurately derives your position based on your velocity relative to the ECI frame, which is just the center of Earth stationary fixed. So no matter if you're going north, south, east, west at any velocity, it accurately derives your position based off of a real timing difference, the same way that sonar does. And actually, the range measurement equation for GPS is the same as the sonar equation for the range measurement equation. The only difference is the speed of light is replaced in the sonar version with the speed of the wave in water with the variable a instead of c. So it's literally identical. It's not a leap. It's exact analogous. It's literally the backbone of sonar and how waves propagating through a medium and relative motion works in said medium.
Doesn't it use the sonar equation? Actually?
Yeah, that's what I said. It's the same equation, same exact equation.
It's the same equation.
It's going to account for the rotation of the Earth as well during transmission.
Yeah, but it doesn't change the fact that it's
even if it did account for the rotation of the Earth, right?
It does.
Even if it did, it still accounts for your velocity. Independent of whatever rotation value may be.
That's basically saying, it's the equivalent of saying the ECI frame is here in my room. It's centered on a disco ball. that I have hanging from the ceiling. So this like the center of this disco ball anchored in my room, which in the disco ball is held fixed, right? The disco ball is rotating in place, but there's still a fixed grid, and within that fixed grid, I can measure my motion relative to that fixed grid, and I'm making velocity corrections for your motion through it, just like you do sonar in the fixed grid of the body of water it's moving through. It's literally the same. That does not respect. Ron Hatch and Ruyong Wong have a whole paper about it, about this very problem. That does not respect Einstein's theory, and yet it works exactly.
So when they do this, right, it's a geometric range that you end up calculating. So that
What?
from the time of transmission to the time of arrival of the signal, you're just dealing with the rotation of the Earth in the ECI frame, and that is it, basically. There's no C plus or minus V or anything like that. It's just purely caused by your rotation.
It's C plus or minus V with respect to the ECI frame.
It's with respect to your velocity. Otherwise, the distance would be off, dog.
So the rotation, the amount you move is related on your velocity.
It would be the rotation plus your velocity in any direction.
C is only constant in the ECI frame, within the GPS system.
Yeah.
It's not constant in all frames. Only in the ECI. Yeah, it's not constant in all frames. It's only constant in the ECI frame.
Yeah, but so you do your calculation in ECI. Yeah. You still have to rotate. You still have to rotate your position.
So Daza, there's still no difference in the sonar equation and the GPS equation. Like it derives your velocity relative to the medium. That's the point. It doesn't matter if the Earth is rotating or if it's stationary. Your plus or minus velocity, in addition to whatever that correction is also accounted for in the timing difference. That's what allows it to be nanosecond accurate.
Yeah, like if the Earth wasn't rotating, it'd still be the same. You just wouldn't have a rotation.
You're not even saying anything unique. You're just reiterating GPS and trying to like make this about ball and stuff. Nobody cares.
You don't.
The rotation doesn't matter
anywhere in GPS, right?
Yeah, the road, dude. But the thing is the rotation of Earth, like that component, that's just a component you add to the end. It doesn't even matter. You can add or subtract that component out, and it's still the baseline of the measurement is C plus or minus V with respect to ECI frame. And you can't.
No, there's no C plus or minus V.
Dude.
Your velocity does not come into the GPS range equation.
It's a real world timing difference.
Yes,
velocity doesn't have to come into it. Hold on one second. It comes in through the timing difference, the same way that the sonar equation does. If you're disagreeing with what we're saying, you're disagreeing with how sonar works. And that's ridiculous. So let's just take a step back. Let's just take a step back and acknowledge that the sonar range measurement equation works. It derives distances based off of timing differences relative to the medium that it's propagating in. Right? Does everyone agree on that? Does everyone agree on that? Does everyone agree that the GPS equation is also the same equation, but instead of using A for the speed of sound in a medium, it's using C for the speed of light in, quote unquote, nothing. Right?
Yeah.
Everyone agree? Okay. So that same system, think to a coherent timeline, GPS time, is deriving timing differences based on you traversing a distance and how long that signal takes to get to you. That is the C plus or minus V in the ECF frame.
Yeah, just like the sonar.
It's not C plus or minus V.
No, yes, just like the sonar equation takes the signal going off of your boat emitter and it bounces off of, a whale. If that whale is moving away from the sonar wave during the time in which the wave is on its way there, it's going to have a different signal return than if it was stationary, and that's going to get picked up as a real world timing difference, and it's going to be so therefore the timing is going to be dependent on the velocity of the whale, which is the receiver, which is you.
No, so if you're pinging a whale, the response time is not dependent on the velocity of the whale.
Yes, it is.
Yeah, okay. You're fully disagreeing now with the range measurement equation that you just previously agreed with, and the GPS equation. And honestly, I would rather talk to zzpop and Tapioca Weasel, because you're just doing a rigmarole. This is ridiculous.
He's just saying nuh-uh after saying
just agree to it, and then on the back end you're like, but then on the back end you're like, but nuh-uh. That's ridiculous. We don't need that here.
So at the time the reflection happens in sonar, right? You have a distance between you and the whale. And
it's derived off of
the velocity of the whale
so.
does not determine the time it takes for the echo to come back.
Yes, it does, because the time,
right.
the packet.
Okay.
The packet
Then GPS doesn't work. Then okay. How about that?
Well,
no. Just finish the sonar one first, right?
That's ridiculous, dude. Okay, 10 seconds later, you get a different ping. You get a different distance. Okay,
yes,
which means
because it's
you're
moving
going at a
towards
certain
you, right?
velocity, dog. What are you talking about?
Right.
That's basic.
So you might be misunderstanding what I'm saying.
This is so fucking gross. Yo.
So here's what I'm trying to say, right?
Yo, Jazza, we're actually not even talking anymore.
The wave propagates out, hits the whale. So the wave's traveling at the speed of sound in water, right? And it's got a particular distance that it travels at before it hits the whale. Then it's reflected back, and it's got a particular distance to travel back. That distance to and from is not dependent on the speed of the whale. But the
then you're
time.
retarded.
Yeah, it is, because the whale's moving away from it, and it takes longer for the wave to get to it. That's how the distance is derived based on the timing interval.
Yeah,
that's literally
but at the time,
which means that the whale had a velocity.
Dude, you can't say yeah, and then be like, but no, it's different. Like, this is ridiculous.
I'm done talking. The wave.
I can't even.
You're measuring.
Yeah,
you're measuring.
Well, he's just trying to hijack the conversation with Weasel and Pop, so that
every time.
Yeah, I'll let you go.
Yeah, we're literally talking to zzpop and
zzpop, Tapioca. Could you tell Dazza what's going on here? Like, you don't agree with Dazza, do you? Both of you?
I'm not gonna lie. I have not been listening to the live VC. I have definitely been jacking myself off in some text chat, because
what?
I'm very fancy.
He's joking, but come on, dude. Don't be a degenerate.
Anyway, zzpop, what's up, man?
What's up?
Do you agree with the measurement equation being equivalent in GPS and in sonar? Just real quick.
Sorry, you cut out for a sec there. I had a comment on sonar, though. So Alan brought up the question of what is different between sonar versus light. With sonar, there's a clear preferred frame of reference. Let's say the water is still. There's a timing difference between, like, if one submarine is signaling the other, whether or not the signal's going from the stationary one to the moving one, or the moving one to the stationary one. Like, you could tell if you are moving or not in a submarine by looking at timing.
This isn't about cinematics, bro. It's about the actual timing difference to derive a distance. That, like,
he's agreeing.
He's agreeing.
Yeah. So the question is there anything that is different about light? I would agree. No, I'm quite comfortable with this framework of space is filled with a dielectric medium. Light is a real physical propagation through it. I'll point out one difference, though, between these two scenarios, which is that in the sonar scenario, the waves are perturbations in water, and the submarine is not made of perturbations in water. It's a completely different physical material, because not everything in the universe is made of water. And we know that as the submarine moves through the water,
right, but it's the same principle, though.
Within it. No, because here's where things diverge, though. When we're talking about the fundamental medium, of which particles, protons, electrons, whatever we think those are, let's say those are sort of stabilized energetic oscillations in the fundamental medium. The analogy
a different timing difference, right?
The analogy is not a submarine with an independent clock moving through water that it itself is not part of. The analogy would be a stabilized structure of vibrations and waves moving through the water that is sending out other waves, as a sonar signal.
You're introducing additional non-factors to not reconcile the fact that GPS is the exact same system and derives a real world time difference based off of your velocity. It functions the exact same through same exact principle. You're making a special pleading to say that because we're made of ether or something, we therefore can't make a measurement with it. But GPS works. Interferometry works. The Sagnac effect works. The linear Sagnac effect works. None of this, like what you're saying, doesn't compute. It's not. You can't be like, yeah, but it's made of a different material. Who cares? Does GPS work or not? Does it derive the same timing differences based off the same principles or not?
Yeah, I think the problem is that GPS does quite literally use the sonar equation. It just replaces the sound speed with the light speed and then calls it good. And the fact that it using that equation without adding extra terms comes up with the correct answer, just like sonar does, means that it literally is a sonar system in a different medium.
Right. Well, I mean, it's just like Coulomb's law and Newton's law. The same. You can replace the variables. It's the same exact.
It's not even replacing a variable. It's just changing the letter because C is the sound speed in ether.
Right. I'm just saying in terms of an analogy for zzpop.
Well, he understands.
Well, I don't know a ton about all the details of how GPS works, but I mean that would be circular motion because the satellites are in orbit, and the Sagnac effect is rotational motion. Right. So I don't think either.
It derives your velocity on the ground relative to the ECI.
And, well, this is a side note, zzpop. Like, let's not focus on this yet, but just as a side note, GPS actually has to make Sagnac corrections.
Yeah, 13 clock corrections, by the way. Or is it meridian corrections?
I thought GPS was just triangulating, just like
no.
if you just have
it's 4.
It's sending out timestamp signals to a receiver. And the receiver is based off of the timing differences, where it's at after it gets 2 or 3 signals or whatever it is. But yeah, those timing differences are based off of motion relative to something.
Through the ECI frame.
If I just had 4 like radio towers, then like I could locate my position, right, relative to them, using GPS.
Right.
Sure.
Relative to now, and then you take another measurement 10 seconds later, and then there's a timing difference because you're 10 seconds further away from when you first pinged, right? That's how you derive your velocity.
Isn't GPS only giving you the velocity in relation to the satellites? I didn't think it was.
It gives it in relation to the ECI frame. So what it does, right, is it sends out an encoded packet, just as Alan said, and it works just like sonar. It goes back and hits a target. Now, sonar, of course, will allow for a reflection back because that's how it reads it. That step's not required in GPS because you can just read it from the receiver at that point. But either way, that real timing difference, you can treat it in terms of a Doppler shift, or you can treat it in terms of a real velocity. Either way, they both cause the same thing. Both create a real world timing difference. And Doppler shift is dependent upon motion of the receiver. And so when it does that, right, it does it with respect to the ECI frame. So in your illustration, how you were talking about, there's a fixed pool of water. That fixed pool of water is the ECI frame in GPS. GPS uses the ECI frame as the bathtub, and it uses
the Earth.
The ECI frame is the center of the Earth.
Okay.
So with respect to the center of the Earth, now they treat the Earth as rotating. You could also treat it as non-rotating. You just have the universe rotating around it. Either way, that doesn't change anything of the fundamentals of the equation. You just add a component for the rotation, but it's
actually do a Lorentz rotation for it specifically from the ITU. You can read about it. That's the quote unquote Earth rotation correction. And if you don't account for it, you're off by 30 meters or whatever. Our buddy Eric still works in GPS and programs and stuff, and he knows all about that. But it's actually not even it's not even a Lorentz boost. It's a Lorentz rotation, which is different, but it still creates a timing difference. So it's not a timing correction. You know what I'm saying? Because without that rotation, you don't get you would be 30 meters off. They say so.
Well, either way, I mean, you're just like I said with the disco ball. Yeah, with the disco ball, it doesn't matter if the disco ball is rotating or not. Whether you add a term to the total motion or for the rotation of the disco ball or not, you still are referencing a fixed grid, which is the ECI frame. And so in that ECI frame, if there's a spinning ball that objects are riding on, or if there's not, everything, both the ground and the objects on the ground, are moving through the grid relative to that fixed grid, which is centered on the center of the Earth. And so in that frame, in that fixed grid, you have real velocity of real objects. And when that time-stamped packet goes out to them, it will arrive at different times based on whether those objects are sitting still relative to when the packet was launched over, I think it's like nanosecond scale that it takes for them to get there. But whether that object was sitting still or whether the object was moving towards or away from the satellite when it sends the time-coded packet will change the timing difference. And so GPS can measure your position and your speed, by the way. I don't know if you've ever used Google Maps and it tells you how fast you're moving. But all that's derivable because it is literally just using the sonar equation.
GPS derives speed from, it can do it two ways. So it can do it by directly comparing two locations and working out the delta. But the most accurate way, so all these GPS-based speed meters use Doppler of the satellites to determine the speed of the receiver.
Yeah, so GPS is doing velocity with respect to this frame, a frame that is calibrated against the
Doing
Earth.
time
But
with
it's
respect to that frame.
right. And the fact that it works shows that we can treat the Earth as a rest frame. That rest frame rules of physics work out well treating the Earth as stationary. That doesn't say whether or not you could also treat other frame of references as rest frames. Like, this doesn't say anything on its own
True.
about whether or not a system.
You're missing the
Understand
point.
Well, he's actually
Treating it
he's actually
stationary
just
or
agreeing with
not,
Ron Hatch there. Ron Hatch
treating it
agrees with you.
stationary, treating it stationary or not, it still derives a velocity difference based off of the timing, which is your velocity. Otherwise, it doesn't get the correct positioning.
Yeah, that's the
The
point. It's a red
principle doesn't
herring to talk
change.
about the rotation. Like if Earth's rotating
Yeah,
or it's not rotating, the equation doesn't change.
yeah.
Well, your velocity
If you solve, if you solve it in ECI space, it doesn't change.
If your coordinate system is timing dependent, right, and you have a rotation to it, right, it's like just the math. Like let's just say the Earth is stationary for reals and we know it, but we have a rotating coordinate system that we're going to apply it to. Okay, to make all the motion and measurements fit that coordinate system, you just add that correction to it. So it doesn't even matter if it's rotating or not. Like nobody cares about that. The point is that it derives your position plus or minus your velocity through the timing difference the exact same way sonar does. That's what is in discussion here. Every time you go to speak, you bring up the most irrelevant point of the conversation.
It's a red herring. Yeah, that's yeah, and that's not a point of contention, by the way. Like that's just a fact. It literally does use the sonar equation, and it literally does depend upon the real motion of the receiver while the packet's traveling to it through space. Like if that receiver moves while the GPS signal's on the way, it will be a different timing than if it was sitting still. And relativity literally says in Einstein's 1905 paper, it says that the speed of light is not dependent upon relative motion between an observer and a source.
Yeah. So I think I understand where you're coming from now. So in the sonar equation, the sender's velocity impacts the return path. So your velocity doesn't impact the time of flight to the target, but your velocity towards the target impacts the time of flight back. So you have to remove the distance you've traveled during the time of flight to work out what the true distance was. And GPS is similar in that the time of flight of the packet, based on the time you determine it was sent and the time it arrives, during that time you have to allow for the fact that you have moved, and the primary motion is rotation of the Earth, that you have moved in that direction and must allow for the fact that you have moved during transmission so that you can correctly
Yes, but okay, let me spell it out explicitly, because the last thing that I said maybe didn't hit home. The reason that that's important of what I just said about Einstein and the way that this works in the ECI frame. This only works in the ECI frame. It keeps C constant in the ECI frame because it's C plus or minus V of the receiver's motion. It doesn't mean that the wave's traveling at some speed other than C. It's still traveling at C, but there's a plus or minus V of the observer's motion. However, if you were to transform yourself from the inertial frame of the ECI frame to the inertial frame of one of the observer, for example, because you can create any arbitrary inertial frame anywhere you want, as long as you're moving in linear motion. If you then are the observer and you are pinging the satellite, or the satellite's pinging you, and you calculate the speed of light in this frame now, it's not going to allow for C to be constant and respect Einstein's postulates, because Einstein's postulates clearly state that the speed of light is not dependent upon relative motion between an observer and the source. And so if you transform out of the ECI frame to either the satellite or the receiver frame, now all of a sudden you have to have a different wave velocity in order to create the timing difference, because if I am a stationary observer, right? So I'm the observer frame, I'm a stationary observer, and there is a satellite moving towards me, right? And it emits a wave. The only way I can make that timing difference change, since I'm stationary, is if that GPS satellite carries a velocity onto the light wave and adds V to the C. So in the frame of the observer, the receiver, it has to be C plus or minus V. In the ECI frame, it doesn't, because C is constant in the ECI frame and the observer is literally truly moving. But based on special relativity, we are allowed to transform to the frame of the receiver. And in the frame of the receiver, where the receiver stationary, the only way you can create the timing difference, the only variable left, velocity, distance, and time. We know that distance is not changing because we're stationary. We know that time has changed because there's a timing difference. The only way to get that is through a speed change where C is no longer C. So that's why it doesn't respect special relativity.
Yeah. Wow. That's really good.
I have one more thing to add real quick about the rotational effects in special relativity. So special relativity actually makes a prediction for a rotating frame. Einstein made that clear in his 1905 paper. And the timing difference that's predicted for a rotating frame is actually 1/2 of the gamma term. So it's an extremely small effect, and that's not even what's measured. It's what's measured is obviously the first order. It would be the first order Sagnac. So, incorrect prediction there on that. It's like I know that was brought up a couple of times. Rotation, like as if it was going to fix something or change something. So to even use GPS, it's actually based on a classical system. Was it classical physics? The time transformation from ECI to ECEF actually is absolute time. It's a Galilean transformation. What's his name? Not Ron Hatch, but the guy that he was arguing with, who did the GPS and Sagnac effect. It was
Ashby.
What's that gentleman's name? He's a big name in.
It's got me muted.
In GPS. No, I can hear you, but what are you saying?
It was Ashby, wasn't it?
Oh yes, Ashby. Thank you, Neil Ashby. Yeah. So anyway, Neil Ashby talks about that for the transformations and stuff. So none of the again, guys, sonar doesn't matter if you're correcting for your velocity to get the timing differences and stuff. It derives the differences based off of timing differences. So if you need to account for your velocity in addition to the thing that you're measuring, that's fine. Doesn't change anything about the functionality.
So I'll quickly close. I just want to say two things. One is, if you can find me a GPS receiver implementation that adds or subtracts the velocity of light from the velocity of the receiver, I'd love to see it. The other thing I'll say is that in all of the modifications that you do, because of the motion of the receiver, it is the motion in the rotational direction of the Earth that is applied. So the You just need to know, like in the sonar equation, you need to know how far you moved during the time of flight so that you know the true geometric distance to calculate the velocity and the time.
Okay, Daz, a quick question for you. Let's say we're on a carousel. My velocity is I'm stationary on the carousel. My velocity relative to the ground, like to the lab frame, is whatever the rotation value is of the carousel, right?
Yep.
Okay. Now, if I'm walking with or against the rotation, and I'm traveling a different distance, is my velocity the same velocity, or is it my velocity plus or minus the rotation value that I'm going with or against?
Oh, so you're talking about your velocity relative to the carousel. I'm talking about the velocity of the receiver.
I'm talking. Yeah, I have a GPS receiver on my carousel.
Okay.
Like we're talking about the same thing. So what's my velocity? Is it c? I mean, is it still the same velocity as if I'm stationary, or is it my velocity plus or minus the rotation of the carousel with or against?
Yeah. So you're traveling with the carousel. So your velocity from the external observer will be the carousel velocity plus your velocity.
Great. So it's not just the rotation value that it has to account for. It's the actual timing difference based on the rotation value plus or minus the velocity of the receiver, right?
It's the rotational velocity of the receiver that they account for.
Yeah, so in GPS, it's just a timing difference. There's no distinction between rotational or linear. So again, the total timing difference is going to be plus or minus my velocity relative to the rotation of the, it's going to be plus or minus my velocity relative to the rotation rate of the thing that I'm on, right?
Yeah, so they rotate your position.
That's it. That's it. That's just yes. Just yes.
Yeah. So they rotate your position, and the geometric difference in distance due to the rotation is the distance that is used to calculate
and my
the range.
velocity. And my velocity.
No, your velocity forms part of the distance you travel.
Yeah, no shit.
So if your receiver is stationary,
that is the total sum of that is the timing difference for the c plus or minus v that accounts for my velocity. It's not just a rotation value. Like you keep saying that it's just the rotation of Earth. It's not. It would be the rotation of the Earth plus your velocity or minus your velocity if you're going with or against it.
If the satellite was if you were traveling directly in the same plane as the satellite,
we're on a carousel. We're on a carousel.
No, here's what I'm saying.
You just agreed to everything, and then now you're saying that we're on a different carousel, so it's going to be different. This is why I don't want to talk to you, because there's no conclusion. We both agree on the same thing, but because it leads to my position being correct about the medium, you're just obfuscating. I can't. Enjoy.
You won't quite let me finish it, but yeah, it's so in the carousel scenario, the distance change between you. So you want to know the distance between you and the receiver, you and the transmitter, right? So you need to know how far you've moved during transmission, so you know what the actual time of flight was when it arrives, and so what the geometric distance that the light actually took, and that is not dependent on your velocity as such. It's dependent on how far you moved during that period, which is not dependent on the speed of light at all. It's a geometric position change. But anyway.
Let's see here. Sorry,
I mean, I'm not really sure what.
Turn on for a second. Sorry if I'm cutting anyone off.
All this stuff about the GPS has been. I mean, like, there's a clock on the satellite. The satellite's sending signals to the car.
Testing 1 2.
It's measuring the time delay return for signals going from satellite to car and back to satellite, as recorded against the clock on the satellite.
It doesn't even go back to the satellite, though. It's just a one-way measurement based off of the timing of the time the signal was sent from a timestamp from JIPS, and then your receiver timestamp.
I obviously don't know what the algorithm is then.
Yeah, it's all good. It's literally just sonar, like we've been discussing, and as we were talking about earlier, it derives your velocity plus or minus your velocity relative to any rotations that may be occurring. Otherwise, it would give a different distance and it would be inaccurate. So we all agree on that. And that's really cool that we were able to come to a conclusion together.
Check chat, all of you. I just took the time to explain it in text, line by line. That's the full case laid out. If you disagree with what we're saying, then you have to answer my question. Because either we're correct or there's an answer to my question.
I'm glad to know that you've just debunked Einstein. That's quite
GPS. It doesn't have to be with moving satellites, right? It could just be, we could just have like radio towers on the ground.
Yeah, except that there's a Doppler shift coming from the satellite, and they go in and out of range for some reason. That wouldn't happen on a tower.
I mean, my
so please answer my question. My bet is that you're not going to address my question. You're going to try to step around it and ignore it because there isn't an answer to the question. That's the exact problem.
Earth is Life published here. Let me show you again. He went and asked.
So are you going to answer my question? zzpop, you can feel free to answer too, brother. These guys are a little more contentious than you are, but Dazza,
why does that guy come in here and then just say nothing? That's so crazy.
Yeah, Dazza and NASA are not.
Like, imagine your contribution to a conversation was to just take a dump everywhere.
That's right there. No, you guys are wrong. The GPS is a satellite.
But you didn't make any substantial point about how we're wrong. You just absurd nonsense.
GPS is a satellite. GPS is a satellite on orbit around the globular Earth, giving you.
I'm willing to grant all of that.
3D space. Okay, well then you are. Then how can it be? This sonar thing is kind of throwing me. I guess there is a similarity, but sonar is a two-way path, and you got to account for a lot more. Because
well, it's the same equation that's used, and the timestamp, instead of having it have to come back to what was sending it, like in sonar, you have the information needed to decode it in your receiver. So the timing difference is computed on your end. So it's the same exact functionality.
But it's velocity times time, right? That's the range change that you calculate at your end. Your velocity times the time of flight gives you your new position, so you know how long the signal actually took to arrive, or how far it actually.
No, it's actually just the time that the signal was sent and the time that the signal was received. It's literally the same equation.
And
there's no velocity correction in it. It's just timing.
It's giving you the ephemeris, so you know how far away it was at the time. And to locate yourself in three-dimensional space, you need 4 signals, not just 1. So.
Okay, and none of that is relevant though, because we're talking like we're assuming we have all 4, and we're talking about how it's deriving our position based on our velocity plus or minus the rotation value of Earth if we're traveling with or against it. Because it's not just about the rotation value of Earth, right? It's also about our velocity plus or minus going with or against it. Going with or against that would be rotation, right? Like, does it? How does it? Like, can we just get a conclusion on that real quick? Does you guys agree with that?
That doesn't change the speed of light. It just makes your time difference as you intercept it a little bit earlier, a little bit later.
Yeah, let's assume it doesn't change the speed of light. That's totally fine. But it does derive a timing. It does derive your distance based on your velocity plus or minus the rotation value of Earth, right?
Well, you would need 2 positions. You would need its last position. And
it doesn't matter how many positions you need. We have them all. We have all the positions.
So just
no one's arguing
you're just computing your position. You're just computing the position.
NASA, you're making an argument that no one's making.
You're just computing the position you were last, and now you have your new position. You know how far apart those 2 positions are. That's your velocity.
Okay, thank you for sharing.
Based off of the timing difference, right? So it's not just a rotation value. It's also your velocity. That just say yes. Just say no, so that it's clear for the audience.
No, what it's doing.
You think I'm incorrect, but you agree with me, bro. You just talked about the timing difference is your velocity. Yes, that's our position.
But the way it computes the velocity is not to have anything to do with the initial signal coming down from the satellite. It has to compute a position and then some time in the future, probably.
That would be your reference. Of course it does. That's your reference frame for when it starts. Duh. Dude. If it didn't matter, then you wouldn't need another. Then you wouldn't. Okay, hold on 1 second. 1 second. 1 second. 1 second. If it didn't matter, then you wouldn't need an additional measure. You wouldn't need to do trilateration, right? You would need additional measurements. Okay, so let's not just endlessly say nonsense. Let's very simple and straightforward so that everybody can understand it. GPS derives your position based on your velocity plus or minus the rotation of Earth if you're going with or against it. Correct?
No.
Okay.
Yeah,
there's no point in trying to do this. He's not going to agree
No.
with you.
I just wanted to hold on. I just wanted to be clear there, because now the answer is no. But you previously just said that when you get your first signal, right, that's what starts you have your first position, and then you get another signal. The timing difference between those two gives you your velocity. So is that not true?
Well, yeah, but it's not computing. It's computing that on a secondhand basis based on two positions. All GPS computes is your position, and then if you have if you know two positions and the time.
If the first one was wrong, you'd have an incorrect position, though, right?
That's correct. If the first one is wrong, then you would have an incorrect velocity too.
But GPS gives you the correct position, so it's not wrong. So we're both on the same page. Can I just get an agreement, Ben? For the love of whatever you believe in, can we just agree that the timing difference? No. It's not the way that I'm saying it, because the way I'm saying it is what it is. There's a rotation value of Earth that has to be corrected for. They say, right? Do you agree with that?
I think it's a very small position. I don't think they have to worry about that.
Well, if you don't account for it, it's 30. You'll be 30 meters off. So
30 meters.
GPS isn't 30 meters off, is it?
Yeah, you're right, right?
So
if you switch on and off Earth rotation, if you switch on and off Earth rotation, your position shifts by 30 meters roundabout, depending on your latitude. It'll move.
Thank you. So there's a rotation correction, and then there's also the timing difference based on your velocity. Okay, that first measurement that you get, that first timing delay that stamps where you were at when you received that, that's based off of your velocity and the Earth's velocity, right? Does everyone agree? Hands up if you agree.
Yeah.
Everyone agrees, right?
So then what happened?
I hold on a second. I didn't hear anyone. Did anyone? Where did everyone go? Everyone agrees, right?
For a response.
I raised my hand. You just couldn't see me.
Dude, how are you thinking for a response? You know how it works in sonar. You know what NASA just said. We all know that it derives we all know that it works this way. Why is this so hard, guys? This is really...
Because saying yes to you allows you to move one step forward closer to your point, and they can't allow that to happen, dude.
Boys, this is actually profound because if we can't agree on how GPS works as a steelman of how it actually works, then I actually never want to talk to any of you guys again, because that is then you guys will just say anything with no regard for whether it's true or not, and that is that's crazy. So we need to come together with this right now.
Come on, it's NASA.
No. I've known it for a while, but it just going through this right now where we can't even come to a conclusion on something so simple is insane. And then people are like, why don't you write a paper? Why, there's no ether, because nobody will actually admit to anything or come to any conclusion, guys. We all know how GPS works, but for some reason we're like, but it's different somehow for this. It's not.
I don't
guys.
think we all know how. I don't think we all know how GPS works. I've heard a lot of.
You just by happenstance accurately described it earlier.
Well, I don't think
that was a coincidence.
When you say everyone in this room, I've heard a lot of people talk about powers.
Hold on a second, dog. I'm just going to mute you for a second because that's ridiculous. You chimed in to interrupt to correct me on a fucking everyone when I'm talking about the direct people that I'm talking about that argue GPS every day. Like, you obviously know what I'm talking about. So let's just be adults here and say, hey, it does measure your velocity plus or minus the rotation rate of Earth if you're traveling with or against it. Can we just agree? If not, I'm out, man. Because you guys are talking about a different system at that point. That's not GPS. If we're not talking about GPS, we're not even having the same conversation, guys. Are we all on the same page?
Why is this just like so much effort to
Absolute
force
silence,
non-conclusion
dude.
and
All right,
stonewalling?
all right. You guys have a good night. I'm heading off. That's bye. Yeah.
Well, I didn't realize there would be that big an error, 100 nanoseconds.
Yeah, I'm not really sure. I was following what all the disagreements there were, but I thought that the GPS signal went from satellite to car and back, so I was really not understanding how the whole.
It's a time encoded signal, basically, and you work out the time of flight based on. So you know the time of transmission, you know the time of arrival, you know then you can work out how far it travelled.
You have to remember what originally was a military system, and the whole idea was they wanted someone to be able to find their position without giving away their position, so they didn't want any transmission up. It's all one way downward.
So zzpop, would you like to address my question now? Like,
I just want to be clear on something. So GPS would work just with like 4 radio towers on the ground, right? Because once you've got satellites with motion, there's going to be a whole other complicated set of corrections, and I don't really know all the things they do to deal with that. But like,
if you did that,
do this, with radio towers, right?
Yeah, that would just be sonar. That's the way sonar works, because your fixed frame is going to be an Earth fixed frame.
No, with radio signals, not with sound. But yeah.
Yeah, but it would work the same. That would just be an Earth fixed frame. That's sonar, which GPS uses a sonar equation. They just add extra terms for Earth rotation. But once again, here's my question, right? You have in the ECI frame a moving receiver and a stationary receiver that are both pinging the same satellite, okay? Or you just do one at a time. You have a receiver, it pings the satellite pings it. If it's stationary versus if it's moving, they will get 2 different times, right? There'll be a timing difference. Now, if we transform to the frame of the receiver itself,
are they in the same place?
Both of yes, they're in the same spot. Like, we're just doing 2 different.
At the time they receive the signal.
Yeah, we're doing 2 different iterations, or we're doing one iteration for a receiver that's moving in the ECI, and then we're doing another iteration for that same receiver when it's stationary in the ECI. Now, in both iterations, okay, the receiver itself, okay, if we transform to its frame at the moment that the packet is sent, boom, now we do our calculation, okay? We have a fixed distance. It doesn't matter. It doesn't matter if the receiver's moving in the ECI frame or if it's stationary in the ECI frame. If we transform to the receiver frame, because Einstein's theory allows us to do that, in the receiver's frame, there's a certain fixed distance to where the satellite was when the packet got sent, and it's the same either way. So in both cases, we have the same distance, okay? We have 2 different times, though, right? Because we know the the ECI moving receiver and the ECI stationary receiver, in both cases, they get different times. So we have a same distance, we have a different time. That means we have a different velocity. There's no way to use a fixed distance and get a different time unless you change the velocity. That's the problem.
Where do we get a different time? Can you explain that again, please?
Because in the ECI
it's in the same
frame,
position, right?
That's
can
my
I just
point.
clarify?
Yeah, that's my whole point.
If we have 2 receivers, one is stationary in the ECI frame and one is moving, and they are coincident in space at the time they receive the packet.
No, at the time the packet is sent. No, at the time the packet's sent. At the time the packet's sent. That's the point. In the ECI frame, the receiver is moving while the wave's on its way there. While the wave's on its way there, the receiver moves in the ECI frame. But in the receiver frame, okay, in the receiver frame, the receiver that's stationary in the ECI frame is going to be stationary in the receiver frame. The receiver that's moving in the ECI frame is going to be stationary in the receiver frame. They're both stationary. The one that's moving in the ECI frame, what is it going to see? It's going to see the wave from the GPS satellite getting there faster. That's what it's going to see, because the distance
I thought that
fixed.
the GPS satellite was the receiver. Is it not?
No, the GPS satellite is the emitter. The ground, your cell phone's the receiver.
Okay. Yeah. So during the time of flight, you have moved towards the receiver, right?
During the time of flight, the receiver moves in the ECI frame, but in the receiver frame, but in the receiver frame, which is centered on a receiver and an inertial frame, meaning that the receiver is not moving in both cases, what the receiver sees is, the world around it moving, but what it sees is the 2 signals ECI stationary and ECI moving receiver, they see the signals moving at two different speeds. That's the only way you can get a timing difference. That's the consequence.
No, it's incorrect.
Yes, it is, because the distance is
No,
the same.
The light's traveling at the speed of light. The distance gets. What do you mean?
The distance gets changed
No
how?
one gives a
How does
shit.
the distance get
No one-
changed? In the receiver frame, how's the distance change?
No one gives a shit about the receiver frame. The receiver emits a signal. That's all it
Oh,
cares.
so you're literally avoiding the entire point of contention. You're saying no one cares about. Hey, I'm going to debate you about the contentious point you're making by saying that no one cares about your contention. Really smart,
no one
dude.
gives a shit about the receiver frame. Why
I just don't.
The receiver, once the
understand
receiver
this.
emits a signal, it's done its job. No one cares about it
The
anymore.
receiver doesn't emit a signal; it receives it.
Yeah,
Einstein's theory requires you to be able to take the position of any frame that you want, any inertial frame. The laws of physics are valid, and so if you want to transform to the receiver frame, you can. And so in the receiver frame, the speed of light is also required to be constant, but that doesn't work because you'll get a timing difference in the two different cases. Different time, same distance equals different velocity. It's very simple.
Well, no, I don't understand how you're saying anything other than just you can tell what your motion is. The receiver can determine their motion relative to the emitter. Like, yeah. Agreed. Yes. You've got emitters of signals, and the receiver is hearing those signals and using that to triangulate its position. And if it's moving, it's going to receive those signals at different time delays. So it's going to conclude that it's in motion relative to the emitter.
The emitter doesn't matter because the wave gets emitted at a point at the very beginning, and then the emitter continues on through space while the wave that got emitted travels to the receiver. Once the wave gets emitted, we don't care what the satellite does. It could fly and do a corkscrew to Mars if it wants to. It doesn't matter what that does. But the wave,
Can I just say that and you have a big
the wave
fit about
itself, the wave itself has to have a different velocity in the receiver frame in order to get a different time because you have a fixed distance. The distance we are using, just to be clear, the distance we are using is the distance from the receiver to the satellite at the instantaneous moment the wave gets emitted. Okay. And in both the moving receiver and the stationary receiver with respect to ECI, those distances are the same. We start at the same point, the wave gets emitted, and then while the wave is on its way, one receiver moves in the ECI frame, the other sits still in the ECI frame. But from the perspective of the receiver in the receiver frame, the receiver's not moving. So the only way you can get a timing difference between the two cases is if since the distance is the same, is for the wave itself to have a different velocity. It is literally a binary option. Velocity equals distance over time.
Yeah, but you're using the distance from the original frame there.
You're using the distance from the stationary receiver frame.
Yeah.
Or the moving receiver frame, they're both the same distance, right? You only care about the distance to the point the wave got emitted from.
Not in relativity. I mean, like everything you're saying is correct, that if you don't incorporate relativity, then in the frame shift, the speed of light would be different.
So explain to me in a stationary receiver frame how the distance to a point in space gets changed.
Because in the in the moving receiver's reference frame, where they now view themselves as stationary, they also have a different coordinate system. Like they have a different definition of where the signal was sent from.
No, they don't. But no. Because at the moment it all starts, where they're both in the same spot in the ECI frame, at the moment it all starts, right? There's a distance to the point the wave gets emitted from. That distance cannot change if the receiver's not moving.
Well, this is length contraction.
But there can't be length contraction if there's no motion. You don't get length contraction from a signal from you sitting still.
Well, length contraction is what you see if you're looking at something that's moving with respect to you.
The wave, you can't add velocity to the wave. It has to be c. That's the point. Light itself doesn't experience length contraction.
How it's accomplished.
Yeah, you can't length contract the light wave itself.
Well, wait, you do, because that's the Doppler shift.
No,
I mean, you
no,
see
no, you
waves.
don't. Light. No. Because at the moment it all starts where they're both in the same spot in the ECI frame. At the moment it all starts, right? There's a distance to the point the wave gets emitted from. That distance cannot change if the receiver's not moving.
Well, this is
Doesn't
length
say the
contraction.
distance. Doesn't tell you the distance.
But there
It only
can't be
tells you-
length contraction if there's no motion. You don't get
It
length
didn't-
contraction from a signal from you sitting still.
Well, length contraction is what you see if you're looking at something that's moving with respect to you.
The
So
wave you can't add velocity to the wave. It has to be c. That's the point. Light itself
Yeah,
doesn't
this is how
experience
it's,
length
this is
contraction.
how it's accomplished.
Yeah, you can't length contract the light wave itself.
Well, wait, you do, because that's the Doppler shift.
No,
I mean, you
no,
see
no, you
waves.
don't. Light. No. You can never take the frame of the light. That's the one forbidden frame in relativity.
No. I didn't say that you could take the frame of the light. I'm just saying, like, if you're moving towards or away from a light beam, you'll see it
But
as
you're
having
not moving
different
towards or away from it. You're stationary. You're stationary with respect to the point that you're at, right? It's centered on you. Literally the entire world coordinate system is centered on you. Okay. And there's a point over there where a light wave gets emitted from me. And then I hit the play button.
Right, which was emitted from a source that was moving away from you, though, when the source emitted the light wave.
But that's c plus or minus v. You can't do plus or minus v of the satellite and add it to the light wave. That's what you're saying. Without saying c plus or minus v, I'm just telling you what you're telling me. You're telling me that whether the satellite's moving with respect to me or not will determine the velocity of the light wave. And I'm agreeing with you. I'm just saying that's not allowed in special relativity.
Yeah, well, I'm saying is pre-relativity, they would have just said that from a different perspective, the light is a different speed, right? But then the way relativity manages to keep the speed of light the same in all reference frames is to then mess with lengths and durations, simultaneity, and like that's why all that stuff gets incorporated in.
Yeah, but I'm accounting for all that here, and I'm telling you that's not allowed in this case because you are in a stationary receiver frame. In all inertial frames in the universe, the speed of light must be constant. It cannot be c plus or minus v. And you're telling me that the solution is, well, the satellite emitting the light is moving, so that's adding or subtracting the velocity with which the satellite's moving towards me to the light wave so it reaches me faster. That's how I'm getting a timing difference. Because we've acknowledged here that the distance to the emission point is the same in both cases. So once it's emitted, it doesn't care about what's happening after that. It's a light wave traveling through space that's supposed to be traveling at c. You can't just arbitrarily warp space in between me and that point because I'm not moving. So none of that applies. There's no length contraction of a stationary object. So in my frame, where I'm sitting still as the receiver, that light wave that got emitted is supposed to travel to me at c, period. And that means there can't be a timing difference. If I've got the same distance and I've got the same speed, I should have the same time. But that's not what we see in GPS. It works on real world timing differences. It shows that c is only constant in the ECI frame. The ECI frame is a preferred frame for GPS. So it destroys the relativity of simultaneity.
Wow, that's really good. When are you going to publish this?
Ron Hatch already has a paper on it.
Ron Hatch. Do you have the paper on that? Let me see. You have a link to that one?
Yeah, I can drop it.
He had some different views on the why we see what we see in GPS, but he generally didn't agree with what the maths said. So his model was different. The outcome's the same.
Here, I will drop this and I will tag NASA. I will tag DAZA.
His model was different, but the outcomes were the same. No shit.
Yeah. Yeah, it's like Ron Hatch was literally the president of the Institute of Navigation, which is the international organization that's like the world nerds about GNSS. He owned a bunch of patents for GPS. He had a GPS company. He literally created the Hatch filter, which was the filter that was used most often before the Kalman filter came out. So anybody wants to argue that he doesn't know what he's talking about is a retard.
So the Hatch filter is still used. That's for smoothing fade, carrier phase measurement, and the Kalman filter is there for providing a stable converging solution. So they're still both used in nearly all receivers. And his key contributions were in RTK and differential GPS, and ironically, which have very, very low relativistic components in their calculation. As does any receiver. There's essentially no relativistic corrections in any commercial GPS receiver.
So I just got a comment since I definitely need to make sure I'm picturing correctly the situation you're describing. With we're talking about like, okay, if you are moving away from an emitter, then because you're moving away from the emitter, there will be a longer time signal for the signal to reach you. True. In your perspective, you're stationary. Okay, one way you could interpret that result is different speed of light. Fine. And that would be if you make yourself stationary and keep the same distance and the same time at which the signal was released.
Well, if the same distance and same time would be same speed, it's a different time with the same distance.
Right. Yeah. Sorry. It's a different time. Sorry. Let's distinguish between the time duration of the signal versus the time when the signal was released. Right. Because the signal's released.
The reception time.
The
release, the emitter, the emission time is the same, and the emission distance is the same.
Yes. Okay, good. Now I can clearly hone in on this. Right. So the way you can make it so that the receiver is stationary and the speed of light is still c is to make the emitter time earlier. If you need to explain a longer travel time of light before it reaches the receiver, and you want of light fixed,
but you can't change the emitter time because the packet has the time encoded on it. It's timestamped.
Yeah, it's timestamped.
Well, it's timestamped in a particular reference frame, and you would just say, okay, that was their reference frame, but translated into my reference frame, I think that all of their clocks are forward or whatever it is. Like, yeah, of course it is timestamped with the time in the reference frame of the emitter, sure. But I could always just be like, okay, the actual.
No, it's actually in the reference for the ECI frame is where it's timestamped.
Right, but the whole point is if I'm moving, I'm not in the ECI frame, right? So I do get the timestamp, but then I say, okay, in my reference frame, the actual emission time is the timestamp minus some amount of whatever. Because if you're moving, then you're saying that the clock time of the ECI frame isn't the true time, that it's offset.
But we don't even need the timestamp, right? Like that's just the way that we, calculate it. Like in this example, we agree that everything's at the same point, right? In both frames, in both the receiver frame and the ECI frame, and the satellite, the receiver are both at the same point. So we know that they're at the same distance. Now we also agree that in both situations, the signal is emitted at the same instantaneous moment. We agree on that.
No. That's the contentious point right there.
But see, no. But this doesn't work, right? Because you saying that the time is different is one thing, but you saying that we don't agree that the emission occurred simultaneously, right? That's retarded because we know in this case that at time t equals 0 is when it occurs. In both situations, time t equals 0.
In the ECI, it's time t equals 0 in the ECI frame. And the point I'm making is that the person who's moving is going to say, that's nice and all that the signal was released at t equals 0 in the ECI frame, but the entire ECI frame is offset in time. The entire ECI frame is off compared to the true time.
But it's not, because the true time in both situations, at the instantaneous moment that the emission occurs, we are in the receiver frame, and the receiver in case 1 and the receiver in case 2 both agree, okay, a mission start. Like,
no, they don't agree. That's the point of
well, that's
relativity.
right. That's the point. This relativity of simultaneity is retarded because you have to tell me that a GPS satellite that does already make a correction for its own motion, right? It literally has a cesium clock and it uses velocity corrections for the satellite and does timestamping. You have to retroactively, it's literally retroactive. You retroactively wait until you do all your calculation to get the timing difference. You say, oh, we got a timing difference. Instead of saying that this was caused by real motion through space in the ECI frame or by a change in the speed of light in my frame, I'm going to retroactively say that the past changed and that the emission actually occurred before the other one in one case compared to the other. Like you literally just have to change the entire definition of time itself in the way that you are able to know reality. Or you could just take the obvious example that's not retarded witchcraft of Jewish magic and say, maybe I was moving.
And there it is, right? That's the underlying thing that's driving all of this.
Oh, that was an interesting thing that came out there. But
yeah, because Einstein was a gay Jew that married his male cousin.
Yep, there we go. No wonder you're a flat earther, mate.
Yeah, you don't know about that? You didn't know he's married his cousin?
I knew he married his cousin.
Male cousin? Yeah, they were like second cousins or something. I remember right.
I mean, if you go look at the picture,
it's a very hateful thing that you're saying, though.
It's hateful that he married his incest is hateful. Yeah, I agree.
It's the way you're talking about it is quite hateful.
I have every right to criticize a faggot that marries his cousin.
Didn't he come up with relativity before he got married? If I remember right, my timing's a little bit off.
Einstein, though most famous, was far from the only person who developed modern physics. So focusing in on any set of...
He's the one who created relativity of simultaneity, which is what we're critiquing here.
Yeah, I mean, he's most famous that goes with it. It's not like he worked in complete isolation. It's not like these things weren't also being worked on by contemporaries. And then
but do you see that in order to answer my question, you have to say, well, actually, I can't even grant you the premise that in the case one and the case two, where you said we all start at the same time, we all traverse the same distance. I can't grant that because it doesn't work. So I'm going to retroactively go back and say in one case, we actually push it further back into the past and say it actually happened before that. So you're literally bending time.
Not changing the past, because the point I'm making is that the moving observer, if they were always moving at that speed, has forever been of the claim that the ECI frame is offset. Like it's not a retroactive correction. It's just sort of like a permanent fact that in the frame of the moving observer, the ECI clock frame is off, that each frame sees every other's frame's clock as being, off.
Well, you have to postulate that. That's the point. I don't agree with that. I don't grant that because that's retarded, because time is not something that's relative.
It's incorrect. Time is relative.
So,
and your only proof of that would be to say, "Oh my,
real thing."
Yeah. Oh, what's your proof of that? That a clock changed?
Yeah, several clocks.
So you mean like? Oh, so you mean the cesium atom, as it moved through the background medium of space, experienced a change? Experienced a change in its relative impedance that it was experiencing of space itself, and that caused the superfine oscillations of the energy levels in the electrons to alter the rate at which the cesium atom vibrates. And since the clock rate changed, it caused the clock to precess. Okay.
Yeah, except that that's not how
you can accept that a physical clock experiences physical effects when it moves. You have to change all of time and reality itself.
Well, again, explain muons. We see muons on the surface of the Earth.
Okay, wait. I need to get clear. I need to be clear on something here. Is like I'm pretty pro these ether models, and I'm very pro saying that there is we can think of things as there being a single stationary reference frame, the rest frame of the ether, and that when something like a cesium atom is moving through it, is clock slowing. There is a clock slowing effect, and this is the thing that Alan dismissed out of hand of why I was saying that the submarine in the water was a bad analogy, because the submarine isn't made of water. And Alan dismissed this right away of just being like, oh, because we're made of ether and we're moving through the ether, you think that has an effect? Yes, that would be the whole point of my perspective on it. We're made of charged particles. Ether's the fundamental medium of charge. So, yes, I do expect there to be effects at the rate at which a physical clock ticks based on its velocity through the ether. And those effects have to be accounted for, which is why this is not analogous to the submarine moving through water, because the
Yeah, but
submarine
that's what the
is a
Sagnac
completely
effect is, bro.
But see, hold on,
that's
hold on.
rotation. That is
Wait, wait, wait,
rotation.
wait.
We need
Wait,
to
1
distinguish
second.
between linear and rotational. Anyway,
I
but I was just
I
explaining how
I partially
relativity
agree
does.
with you, ZZ.
Yeah.
But here's the thing. When we can measure a single, I believe that electrons are solitons in the ether, little wave packets in the ether. Okay. They're made of ether, right? And in fluid dynamics, when you look at the equations for solitons, solitons experience length contraction because it's an inertial response. When the little wave packet that's made of the medium it's moving through moves through that medium, it pushes the
Yes.
medium ahead of it. It pushes the medium ahead of it out of the way, and the medium ahead of it responds via inertia and pushes back on the soliton, and it gets compressed a little bit, and it's ratioed against the speed at which it moves. Okay, that's what we
It's like a
physically
wake.
see. Yeah, that's
Yeah.
exactly how solitons behave. That's exactly what electrons do. However, you can obviously see if it does that to electrons. That's why the clock frequency of a cesium atom would change, because its electrons would experience this effect as it moves, and therefore its transition frequency would change because there's a finite amount of energy
Why would you do
there.
that?
There's a
would you do
finite
that?
amount of energy present in that atom. Okay,
You have
and
math
so
to explain it?
Yo,
since it
NASA, could you stop interrupting with nonsense? Thank you.
With nonsense, I want the math. I don't
and
want his
so
words. I
since
want math.
it's like
Okay, then look it up.
I'm literally explaining the thing he wants to know, and he's interrupting me to ask me to explain it while I'm explaining it, so I can't explain it. Anyways, as that oscillation occurs, if that oscillation is let's say a set fixed distance, right? Because it's traveling through ether, it will oscillate with this finite energy, fixed energy at a set fixed distance at a set fixed rate. But if that distance changes because the soliton itself is being compressed, it will have a finite fixed energy traversing a different distance, and therefore it'll be in our frame appear to oscillate at a different rate. And so that is why the clocks precess, because their their tick rate, in other words, their tick rate is changing based on their velocity through the ether because of that response. Now, that is for electrons, because that's literally directly affecting the electrons of the cesium atom that is acting as the clock set frequency.
Mhm.
We cannot necessarily just assume that we can extend that to all matter everywhere, because all matter everywhere is not just individual solitons. It's a bunch of solitons, as well as the giant lattice structures that they form, and we have absolutely no idea if the entire lattice of something trillions upon trillions, exponentially trillions times bigger than a single electron, is going to obey that same exact relationship to those same exact ratios.
So I totally agree with all of that. That's actually completely my position on these things. I do think, though, you can use inductive reasoning if you can show that all the known forces inside matter obey certain contraction and dilation effects, that this scales up to a larger system. I'm not even saying you're wrong in wanting to interrogate that, but I think that there's an inductive argument that can be made there. And you're right. Everything we've been talking about has been about charge and light, and that's just the electromagnetic force. So we shouldn't assume that this applies as well to the nuclear forces. But what we do know about the nuclear forces experimentally certainly suggests that it does. The equations we use to model the nuclear forces are nearly identical to the electromagnetic equations, have exactly the same features and mathematical structures that causes these types of clock slowdown and length contraction effects as you were describing in the electric case. I agree. If the nuclear forces were different, then this wouldn't be a universal principle of nature. If we find a force that's different, then it's not a universal principle of nature. But if we go down the list and all the forces obey these properties, then I don't think it's such a leap to say that large scale objects made of nothing but bits that are waveforms, in these underlying fields that all obey these properties would at whole experience these effects.
Well, if you want to apply soliton logic to nuclear forces, that would require you treating all particles as solitons. Whereas, and I'm not necessarily opposed to that. I think that everything's made of the medium, but the point I'm making is in mainstream, they treat everything as actually being a product of real length contraction or time dilation. Time dilation is not real. For length contraction is, time dilation is not. Time dilation is the inverse that's required in order to keep CC. Okay, but if time dilation is not real and length contraction is, that means that there is a preferred frame, which is what you're saying. I agree with you, but that's not compatible with special relativity. So you're simultaneously saying that you do believe
You're
that
saying,
there's this medium and there's this, which,
length contraction is real, time. Sorry, which way did that go?
length contraction is real, time dilation is not. Length contraction of particles can be measured, and we can observe that. Time dilation is claimed to be observed, but it's not time itself that's changing. It's, as I said, the cesium atom is experiencing effects because it's moving through the medium it's made of. And so that's totally different than time. Time itself is not changing because it's just the inertial response. That's what we just discussed. So I'm agreeing with you. I'm saying that there is a medium. It does fill all of space. It is this, we can treat it as a stationary frame. I agree with it. I'm just saying that that's not compatible with Einstein's theory. So you can't simultaneously hold your position and defend Einstein.
So wait, I don't know what you mean by saying that this clock precession difference, which let's say it does apply to all clocks, right? It applies to a clock made of a circuit or resonance of an electron or some sort of resonance of a nuclear process, right? Whatever it is, like
I would
let's
have
just
to
assume
see it.
like
I would have to see it happening to like if they could make like a fully mechanical clock that was like really, 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 really accurate, like accurate enough to where we could put it on a super fast jet and measure its precession if it did precess or didn't. If they could do it with a mechanical clock, then I would probably be willing to grant that it occurs to macro scale matter and not just the particles themselves, individualized.
Look, if you want to talk about a macro clock, I mean, there's spring or something in there that's pulsating, and the frequency of a spring compressing and stretching is the spring constant, which gets down to the material thickness
Right.
and ultimately the electric forces between the atoms in the spring.
But
I mean,
but I'd have to see it because once again, it's like you're presuming that you can extend that concept. I'm saying like I'll have to see the same experiment performed with a mechanical clock of sufficient precision to believe
But
it.
for the sake of argument, let's say we get to a place where we have demonstrated
Sure.
that regardless of the engineering, this really is a principle that universally holds throughout all matter.
Okay.
Clocks slow down with motion to the ether.
Yeah.
What are you then saying is the difference between that?
Okay, here's the difference. The difference is in our case, with moving through the ether, they are experiencing physical forces, inertial responses of the ether itself responding against the particles making up the matter. Okay. That's our case. Relativity says that time itself is something that can be physically manipulated. That is completely different, and that there is no preferred frame. Okay. So relativity says there are no preferred frames in the universe. They don't exist. There is no such thing as absolute space or an ether frame through which motion, could be mapped to, or time can be mapped against. You can't map absolute time or absolute space or a preferred frame. Everything is purely relative. That is, these two ideas are antithetical to one another.
So the next thing we would then need to ask is, even if there's an ether and even if there's an objective physical clock slowdown for something moving through the ether, can that thing detect its own motion? Like, that's the real question then. could a moving clock through the ether that is now experiencing the contraction and dilation effects to itself, right? Because it is moving through the ether, could it detect that? Or would it be mistaken in thinking that it is stationary and
Well,
everything else is moving?
here's your answer. If there is an ether, okay, and it does serve as the medium through which things propagate, okay, then light is not a soliton. Light is simply a perturbation through the bulk medium itself. It doesn't carry mass. I guess if you treat it as mass, since mass is energy, it would have some imperceptibly small mass that would be like something that would be an artifact of measurement if you could measure the vibrating bulk medium itself in the area in which the ether was perturbed as the light travels. That's neither here nor there. The point is it's not made of soliton wave packets. Okay, that's not what light is. That's what electrons are and particles are. Light is just a traveling wave moving through the bulk medium. So that means that if we use a light signal, okay, let's say that it's traveling through like a vacuum core fiber optic cable, okay, and we do an experiment like Ruyong Wong's experiment, the generalized Sagnac effect with linear motion. What is happening is this light wave is moving, okay, and then also the receiver, which is separate from the light wave, right? The device itself, it emits it and it receives it and it measures the timing differences in clockwise and counterclockwise paths as it moves a certain direction linearly, and then it can separate out the two halves of the loop of the.
Oh, you're talking about rotational motion now.
No. In do you not know Ruyong Wong's 2004 experiment with the generalized Sagnac effect, where he proved that the Sagnac effect can occur with all motion?
True. Ruyong.
The title of the paper is Generalized Sagnac Effect. I can share it with you. But anyways, that he worked with a Naval Research Lab. It was actually the second project. They used a figure 8 setup in the first project, and then in the second project they used a parallelogram as well as a conveyor belt. But he demonstrated that you can use the Sagnac equation and linearize it and measure linear motion. And when the device is on a conveyor belt, he could measure the device's motion. That's a linearly proportional first order proportionality with the speed at which it moves. Well, the phase shift is linear proportional to the velocity. But anyways, what this means, the reason, what causes the Sagnac effect? Because if we accept the preferred frame, if we accept an ether frame exists, then the Sagnac effect is nothing more than from the time that the signal was emitted and to the time that the signal was received, the receiver moved through the ether, and the signal had to travel a longer or shorter path. That's all it is. It's literally that simple. The receiver moved through the ether while the signal was traveling, and therefore the clockwise path was longer or shorter than the counterclockwise path.
So,
or in the linear case, it's the same thing. The receiver moved while the signal was on its way. The receiver moved through the ether, and the signal traveled a longer or shorter path. Special relativity says that the path shrank because the device shrank. But I'm saying that if we separate the signal itself from the device, because the device is made of solitons and the signal is just a perturbation through the bulk ether, it has nothing to do with the device, right? The device is just present there to measure it. We know that the signal is in the ether frame truly is traveling a different distance. So even if the device is contracting or not, the physical distance it traveled across that conveyor belt we can literally see that difference on a macroscopic scale. Like there's a macroscopic distance change in the ether frame. So that's what's getting picked up, and that's what's creating the timing difference. That's literally just a preferred frame. That's absolute space. It's no different from Newton's theory.
So yeah, I'm reading up on this, and if they're doing the Sagnac effect, it's with a loop. The light is going around the loop, but there's nothing rotating. It's moving through things that are only ever moving at linear motion. Every segment of it is moving at linear motion.
Yeah.
this is cool. But there
any finite
is
segment it can measure
it's like,
across.
right, but it is still a loop, right? Like it is still light
Sure.
it's going from moving in one way to moving a different
But
way to
what
moving.
happens if I cut that loop open and I take the two ends and spread them apart and make the loop a straight line? Nothing has fundamentally changed.
Well, I don't think that they were able to do any comparison without bringing the ends back together. Like,
Well,
is
because that's
that
how an interferometer works. Like, I mean, that's how the device, like an interferometer, literally, that's how it operates. But I'm telling you, just fundamentally, when we talk about the root cause of a phase shift, the phase shift occurs because the device moved in the ether frame. That doesn't that happens whether the cord is put into a circle or the cord is stretched out in a straight line. If it's moving through the ether frame, it's moving through the ether frame in both cases. Like the cause is the same, the effect will be the same.
so the point I'm trying to make is that what this would show, like you can only do the observation, like you can only actually have a thing to compare if you bring the two ends together. So what this does show is, let's say that there's a preferred frame, right? The ether frame is preferred to a frame that followed the light around the loop or something like that. But like this doesn't answer the question about a singular linear velocity boost in a single direction, right? You know, the difference between, let's take the ether frame and a frame that is moving at a constant eternal linear velocity to that ether frame, right? Not something that's doing loops, but something that just has one perpetual constant velocity with respect to it. Like
Like
this
what?
thing, I mean, just any perspective moving through space. I mean, like this experiment, it's not saying that there would have any difference between doing it on the ground versus doing it on a train.
No, there would be, because what it's measuring on that conveyor belt is it's literally measuring, like when that device is sitting on the conveyor belt stationary, it has a totally different phase constant than when it's moving on the conveyor belt. So it's not measuring its acceleration, it's measuring its velocity.
Sorry, isn't the conveyor? Well, okay, I need to read up more about this then. But isn't
Yeah,
the
there's no
conveyor belt?
acceleration component. It's literally V. There's no A. And it's just so you know, it's also a first order proportionality. It's proportional to V over C. It's not, or, you know, the velocity is not squared. So it's first order proportional. If it was a relativistic effect like length contraction, it would have to be proportional in terms of the gamma factor, which is V squared over C squared, which is a second order effect. Relativistic effects are second order effects. This is a first order proportionality. It's literally a straight line slope. There's a straight line slope on velocity versus phase. It's a straight line, like a diagonal line on the graph.
Are the different sides of it? Sorry, what is the conveyor belt here in the setup?
Are you on you looking at the paper right now? It's like a 3 or 4 page paper.
Yeah, I opened it up and.
So I think it's page 2.
Let me look through that. I was trying to read the abstract of it. Let me go to page 2. Let me see.
Can you share your screen?
Yeah, I see.
And also, just so you know, you could do this whole thing with a Michelson-Morley interferometer. You would just take one of the mirrors, and instead of using a regular mirror, you would flip one of the mirrors to a phase conjugate mirror.
Let me share my screen.
Do you know what a phase conjugate mirror does?
I forgot. Okay, so this thing, right?
Oh, let me look. 1 second. Yes. So if you'll notice that conveyor, there's like a little tray, and then the FOG is sitting on the tray. The FOG is coupled into the optical fiber loop above it, like to the top, or which is to the side, but above in the diagram. The bottom half of that loop, there's an anchor, that red line. That red line connects the wheels. So whatever speed that conveyor belt moves is the same speed that the linear segments of the loop above move. So the bottom half of that loop is moving at the same speed as the FOG itself. So it's literally isolating the top half of the loop from the bottom. It's the bottom half of the loop and the FOG are in the same inertial frame. So what it's doing is that means it isolates out the top half, and the phase difference is purely created through a finite segment of that top half, which is it's actually isolating basically the one-way speed of light in that linear segment.
So this is the question I have here. These wheels, though, are not on the conveyor belt.
No, those are fixed in the lab.
Right. So the thing that we're adjusting is a velocity that is a velocity between different components of this device, like this fog is
Well,
a emitter or a detector.
Yeah, that's what I'm telling you though. So the loop, like the signal has to traverse the entire loop, right? The loop, which is the cable is a fixed length. Okay. The FOG and the bottom half of the cable are moving in unison with one another. So they are considered to be in the same inertial frame. Okay. They're moving at the same speed in the same direction. The opposite half of the loop, the blue part, the blue cord, is moving at the same speed in the opposite direction as the bottom half. So what ends up happening is that there's a phase difference created purely due to the difference in the top half of that loop. And that's what the FOG is measuring when the whole thing is moving. It registers that little graph. If you scroll down just a little on your page. Yeah. So speed, phase difference. Look, yeah, phase difference on the left, and then the speed of the fiber on the right, on the bottom. I mean, so you've got the vertical axis is the phase difference, the horizontal axis is the speed. There's a linear relationship right there. It's 1-to-1. It's first order proportionality, and the equation is 4 pi VL over C lambda. So it's V over C. It's not V squared over C squared. Like a relativistic effect, like length contraction, etc., would be based on a gamma factor correction, which is V squared over C squared proportional. This is first order, not second order.
Well, I think I'm gonna have to go to sleep soon, but I'll give this a read. It's interesting. But the point for me here is that, like, okay, so what you take this entire device, right?
Mm-hmm.
When you're running the experiment, you're manipulating these different velocities here. But you do have some fixed points here, right? The wheels themselves, they're not part of the conveyor belt. They are stationary in this experiment, right? It's the cables moving.
Uh-huh.
Anyway, I need to get a better understanding of everything that's going on. But
Well,
now
well,
I'm
they do the
segmenting
same
the whole
thing. If you
thing.
scroll down one more page, just before you go, scroll down one more page real quick. They do this. Oh, scroll up a little.
Yeah.
You zoom out. Oh, sorry, I zoomed. My bad. So okay, that's a parallelogram. They get the same exact result with this parallelogram by taking the top part up there and shifting it to the left and right, like translating it. The point is the signal has to travel through the entire cable, okay? And the cable is a fixed length. The only way you can get a different distance is if the true distance that the light signal is traversing in reality is a distance through a fixed space that's external to the cable.
Like if you are just making your worldview based on science, then it
The same points in the cable, right? So that's all the same all the time. The only thing that's changed is the cable's position in an ether frame. position in an ether frame. Position in an ether frame or the lab frame. And so since the signal has half of that loop is moving at the same speed as the FOG itself. So it's literally isolating the top half of the loop from the bottom. It's the bottom half of the loop and the FOG are in the same inertial frame. So what it's doing is that means it isolates out the top half, and the phase difference is purely created through a finite segment of that top half, which is it's actually isolating basically the one-way speed of light in that linear segment.
So this is the question I have here. These wheels, though, are not on the conveyor belt.
No, those are fixed in the lab.
Right. So the thing that we're adjusting is a velocity that is a velocity between different components of this device, like this fog is a emitter or a detector.
Yeah, that's what I'm telling you though. So the loop, like the signal has to traverse the entire loop, right? The loop, which is the cable is a fixed length. Okay. The FOG and the bottom half of the cable are moving in unison with one another. So they are considered to be in the same inertial frame. Okay. They're moving at the same speed in the same direction. The opposite half of the loop, the blue part, the blue cord, is moving at the same speed in the opposite direction as the bottom half. On your page. Yeah. So speed, phase difference. Look, yeah, phase difference on the left, and then the speed of the fiber on the right, on the bottom. I mean, so you've got the vertical axis is the phase difference, the horizontal axis is the speed. There's a linear relationship right there. It's 1-to-1. It's first order proportionality, and the equation is 4 pi VL over C lambda. So it's V over C. It's not V squared over C squared. Like a relativistic effect, like length contraction, etc., would be based on a gamma factor correction, which is V squared over C squared proportional. This is first order, not second order.
Well, I think I'm gonna have to go to sleep soon, but I'll give this a read. It's interesting. But the point for me here is that, like, okay, so what you take this entire device, right? When you're running the experiment, you're manipulating these different velocities here. But you do have some fixed points here, right? The wheels themselves, they're not part of the conveyor belt. They are stationary in this experiment, right? It's the cables moving. Anyway, I need to get a better understanding of everything that's going on. But
well, they do the same thing. If you scroll down one more page, just before you go, scroll down one more page real quick. They do this. Oh, scroll up a little.
Yeah.
You zoom out. Oh, sorry, I zoomed. My bad. So, okay, that's a parallelogram. They get the same exact result with this parallelogram by taking the top part up there and shifting it to the left and right, like translating it. The point is the signal has to travel through the entire cable, okay? And the cable is a fixed length. The only way you can get a different distance is if the true distance that the light signal is traversing in reality is a distance through a fixed space that's external to the cable. Because the cable length never changes. The signal starts and stops at the same points in the cable, right? So that's all the same all the time. The only thing that's changed is the cable's position in an ether frame or the lab frame. And so since the signal has traversed a different distance in the lab frame, that's what creates the phase shift. But if I was to be inside the frame of the cable itself, I shouldn't expect to experience any phase shift because the cable is always the same length. And if you go up to the very top page, the page 1, top right column on page 1, he makes a crucial note here. He says, our experiments, that first paragraph, our experiments are different from the Piezo type experiment, drag experiment of a moving medium, In the Piezo experiment, there is relative motion between the light path and the medium. The result of the Piezo experiment is dependent on the refractive index, and the drag coefficient 0 when the refractive index is 1. In our experiments, as in this in the FOG, there is no relative motion between the light path and the medium. So there's no relative motion.
The cable.
Right, because the cable is the medium. It is the light path. It's the same. It's 1-to-1. So, and they tried it with cables of different refractive indexes, and changing the refractive index had no effect on it. It's all the same. So that means that since there's no relative motion between the light path and the medium, if the medium or the cable is always the same length and there's no relative motion between the light path and the length of that cable, but I'm still getting a phase shift somehow when the cable moves in the lab, that means that the true distance that matters is the distance through the lab. And that's the only thing the experiment sees. So there must be some kind of medium, some kind of preferred frame that's external to the cable that is truly the thing through which the light is traveling.
But there is relative motion here between this length of cable and then the source and the detector, because they're not moving with the length of cable here.
Okay, so if the top part of the cable moves, okay,
yeah,
let's say the cable is 1 meter. It to travel from source to detector, it has to travel through a 1 meter cable. No matter what happens, that light signal is still traveling through a 1 meter cable. How can you have the light signal traveling more than a meter through a 1 meter cable?
You can't. I don't know what you mean by why it would be traveling more than that.
Well, that's what creates the phase shift, is because it's traveled a different distance.
Oh,
that's what the Sagnac effect is. Like literally, the distance has changed. So the cable length remains 1 meter, but when we move it, if it moves while the signal's traversing its length, then we get a phase shift, because actually the signal just traveled like 1.01 meters or something. And so now we know that, so this device is not actually measuring the relative motion. It's measuring absolute motion, because it's actually measuring the distance through some frame that doesn't care about any of this. It's some external frame that's ever present in the system, which is the ether frame. That's literally what George Sagnac concluded. That's how he was actually proving that Einstein was wrong about the ether when he came up with his experiment with the rotating table. This is just, it has extended it to linear motion.
Yeah, I get that this segment of wire here has just linear motion, but it's a different linear motion than the source and the detector. So there's light going from the detector through the wires here that are stationary in the lab frame, and then entering into a cable that's now moving with a velocity relative to the source.
Well, but there's no relative motion between the light path and the medium. So once again, if the light path is if the medium is 1 meter, then the light path is 1 meter. And if the light path is 1 meter in both cases, how can you get a phase shift?
The light path is, well, I haven't yet had time to do this in a lot of detail. I mean, it's some Doppler shift that is occurring as light goes from source.
Well, the source and detector are both stationary. The source and detector are part of the same frame.
Right, but it's entering material that's in motion relative to the source, which produce that frequency of light.
But if it's in motion, then would there not be a different distance? I agree that part of it is in motion relative to the source, correct. However, the path it's taking in the frame of the device, or just let's say the cable, the path it's taking through the cable is always the length of the cable. So you have to reference something else other than the cable in order to get a different distance term. And you need a different distance term in order to get a phase shift. You can't just use the same distance over and over and expect the result of the equation to change.
So you put this on a train.
Yeah.
Right. Do the same experiment on a train. Are we going to detect the motion of the train, or are we just going to detect the difference in motion between the source and the detector versus the cable
This
is moving with
device by
respect.
itself would not pick up the motion of the train. But what you would have to do is you would have to alter it in such a way that, because essentially, if you try to make an analogy, then the train would have to be like a part of that loop, and then separate from another part, like where the source and detector are, or in the above case with the rotating part, like the train would have to be one half of the loop and you'd have to be another half. You'd have to just do something like that to make it analogous. In order for this method to detect a train moving just by sitting it on the train and letting it, like starting out stationary and then the train moves and then getting a different phase, you would have to have it set up to where it's open-ended, right? So this is a closed loop. You would have to cut the loop open and then measure it at the ends and have the whole thing translate through the ether frame, and then measure the signal at the ends as it moved. Because what would happen is if you measured the two ends, as if the loop was cut open, if the line was stationary in the ether frame, you'd get one reading, but then if the line was moving through the ether frame, you'd get another reading because the endpoint would be at a different spot in the ether frame. So the closed loop will never be able to detect linear motion purely by itself. What this is doing is showing that linear motion does cause a phase shift, but this is still being measured internal to the loop. You'd have to open it in order to do that. But we know it would do that because it's only any finite linear moving segment that creates the phase shift here.
Well, thank you for sharing this. I will take a deeper look at it. We'll loop back around on this at some point.
No worries, bro. The mainstream answer, just so you know, I'll tell you, there was an experiment real quick. Dufour and Prunier, Dufour Prunier, Dufour and Prunier. They did an experiment series in like the late 30s and then the follow-up in 1942. Okay. They did a Sagnac type experiment where they had three cases. They had the emitter and detector on the rotating table. They had the emitter and detector mounted to a stationary wall in the lab, and then they had a part on the wall, part on the table in 1942. Okay. They did a Sagnac type experiment where they had three cases. They had the emitter and detector on the rotating table. They had the emitter and detector mounted to a stationary wall in the lab, and then they had a part on the wall, part on the table. And in all three cases, when they they spin the table, right? In all three cases, as long as the table was rotating with the same velocity, they got the same phase shift in all three cases. And they literally, in their paper, they go through they explain like what's expected under relativity, and they expect what's expected under Sagnac's theory, and how the expectations and predictions diverge from one another. That's why they did the experiment. Sagnac predicts you to get the same in all three. Relativity predicts you would at least one of them would be different. They got the same in all three, and they actually showed the numerical difference as well when they math it out. What the numerical difference would be? It would be like a factor of it's like a factor of 10 or something, if I'm not mistaken. I'm recalling from memory right now. But anyway, it's a very perceptible difference that they should have measured and they didn't. And what they did is they made this experiment to address the contention of Paul Langevin, Langevin. Paul Langevin basically said, oh, well, if we just, instead of being in the frame of the detector, if we just pretend that we're in the frame of the center of the rotating table, which is the only point on the table that doesn't move or rotate, is the center axis of rotation, and then we transform everything into a cylindrical coordinate system that's symmetrical about that point and measure all the motion with respect to that center fixed point, then we can predict it correctly. Well, first of all that's doing is sneaking in absolute space because you're creating a fixed point in space that all this is relative to. But second of all, no measurement ever takes place at the center of the table. The measurement in reality takes place where the observer is, which is the detector, and the detector's on the rim of the table. And then so they literally, took it a step further and said, okay, we're going to put the detector on a fixed wall and see what happens. And like I said, a detector emitter fixed wall, detector emitter fixed table, or spinning table, or a mix of the two, all three showed the same exact result. And so it was shown to be a refutation of Paul Langevin's postulate. And the only invocation that people have even really tried to show for the answer to the generalized Sagnac effect here is to try to use Langevin's treatment, where they create that fixed coordinate system at the center of this rotating loop in, on page 2, and make all the distances with respect to that fixed center point where there is no rotation. But like I said, we already know that doesn't matter, because if my emitter and detector are fixed to the lab wall where everything's stationary, or if my emitter and detector are fixed to the rotating table, if I get the same exact result in those two cases, that means the only motion that matters is motion through the ether.
Well, we'll definitely revisit that, but interesting stuff. Okay, thanks for all that. I didn't know about this linear Sagnac effect test. I'm getting very tired, sorry, but
Word,
I
bro.
saved the paper. So word, and yeah, so peace for now.
Good talking with you, man. I find it interesting you came to kind of like the soliton idea, independently or separately or whatever.
Yeah, we could talk more about that some other time. It's a very cool model. I think one very worth exploring. All right, peace.
See you, dude. Like 2:30 in the morning over here. Sheesh. I need to go to bed too.
So this was another. Oops. Dang it. There we go. Or maybe I should do it from this one. Okay. All right. So before we look at the Wang experiment, we're going to look at Sagnac's apparatus, his configuration. So earlier in special relativity, it was put forward that any closed polygon.
What? What are you talking about?
Yo, Andrew, you're hot, micing. We were told that any uniform transitory motion, his equations would apply. So if you're in an inertial frame, the speed of light is going to be the same. And as a consequence of relativity, you're going to experience a little link contraction time dilation as a function of the square of your velocity. So what Einstein says, that it doesn't matter that this configuration isn't symmetrical. It can look like this. It's totally fine that the area that light travels makes a non-symmetrical polygon. And as long as it's in uniform rotation, that his equations should apply. So if you were to apply Lorentz symmetry to this, and you put an observer at the center of the device, and you put an observer at the rim, and you said that the angular displacement, due to that motion of the observer along the edge there, is going to cause a fringe shift pattern. Or well, actually, because they're inertial observers, they're both going to predict that the speed of light is the same. So as this apparatus makes its rotation, and because we're not using absolute space to assign for imaginary velocity vectors, we're not preserving absolute space to make the measurement with respect to that. So when this light completes the circuit going with and against the rotation, it's going to complete it at the same time because of the constancy of C, and because the frame as defined by an observer at the rim and one at the center are going to be inertial as defined by Newton's equations and by Einstein's, following that logic, right? Because if you extend any portion of this circle to infinity, it makes a straight line that doesn't deviate much from linear. And that was the whole rationale behind, putting that in the theory, which, logically tracks, it makes sense. So relativity theory actually predicts that there's going to be no fringe shift pattern. And because Sagnac measured a fringe proportional to the rotation of the apparatus, he said, I falsified relativity theory, et cetera, luminiferous ether, optical vortex. When he described the optical vortex, what he was describing and the rationale behind it was he was saying like, well, the ether must be entrained in the earth. And then within the earth, there's, little pockets where when you're in motion, you're going to create a vortex that's going to be, measurable, right? So that's what he was putting forward with that description there. So on Einstein's terms, he falsified the theory as it was put forward. Now we'll get to the solutions that were put forward here and the history of all that. But this is just to start us off with the first experimental falsification of it, right? And we already talked about the configurations. So a Michelson-Morley interferometer, or the classic L shape, or an orthogonal interferometer, sometimes they're called, or a classic interferometer, etc. Right, is just a right angle. And they say that this one is for measuring linear motion, but it can't do that because link contraction time dilation. And then we have the Sagnac configuration, which is a closed circle most of the time, but it can be a rectangle, triangle, doesn't matter. It can even be whatever shape this is. It's all good. And it will produce the angular displacement amount, right? And they say that that one's good, but the other one's bad, even though it was experimentally shown in 2004 by Ruyong Wang that when you have an apparatus and you measure just the effective moving part of it, right, then you will get a fringe shift pattern that's proportional to that motion. So the apparatus is making the measurement with respect to itself. So typically these gyroscopes are wound in a coil around, a fixed point, and then they say, in that configuration, they're like, oh, that's that rotational one. That's the one that measures angular displacement, right? Now, what Wang did is he unwound the gyro, came up with a configuration here where it has a linear section at the bottom. That's what we're looking at. And then it has two sections over here that move. The motion of these two sides cancels out. The bottom part's stationary. And the calculation and the prediction is only done with respect to the delta L, which is the effective length, right? And then, so instead of the full length of the apparatus, it's with just respect to this portion here, just this top part that moves. So some people will say, well, it was with respect to the detector or the station or the bottom bit, et cetera, et cetera. Well, if that were true, then you would have to use the full length of that. You would have to add more length to the L. You couldn't just use the delta L from the top to predict the fringe shift proportional to just that top portion. So he measured explicitly uniform transitory motion, not in a rotation, right? So this is just rectilinear uniform motion. When we're looking at the graph here, where he's measuring the fringe proportional to that velocity, falsifying the postulates of special relativity about relative motion and the constancy of C. Otherwise, the relativity predicts that there's no fringe here. We have an inertial observer here at this end of the apparatus, and he's sitting at the end here. He's an inertial observer, and then we have an inertial observer here, and these two are in uniform motion. So relativity predicts zero fringe for these lads, and if it does, well, the fringe that it predicts with the function of the square of the velocity, right? That gamma factor correction or contraction, sorry. So link contraction time dilation would predict a much, much, much smaller fringe than this. It wouldn't even be possible for that theory to extrapolate the velocity that this was moved at to produce that fringe pattern, because the special theory of relativity is a theory of second order corrections, meaning that they're not going to be proportional to the cause of what's causing the measurement, right? So that first order effect, that velocity would be the first order effect, and that first order effect is measured in full in the fringes here, right? So if this was a second order effect, the measured fringes would be much, much smaller, and that would be an indication that relativity theory is true. But it's not. It's proportional exactly to the velocity. So it's outside of the confines of relativity to provide an explanation. And of course, we have the configuration up at the top where he's doing it with against the rotating wheel on the other side of the interferometer arm. It's just, anyway, my favorite one is the bottom one here, the parallelogram. That's pretty damning. So just to recap here, with the generalization of the Sagnac effect, what Wang is showing here is it doesn't matter if light's at a right angle or a circle, it will measure velocity proportional. So what that means is the measurements from Michelson-Morley stand as first order measurements and not as a measurement that produced a zero fringe and then would require a Lorentz transformation out of it to say, well, the reason you can't measure it is because you contracted by this amount. Okay. So you would think like there's a cohesive history, or that you would think that when a man published a paper of that magnitude in 1913, experimentally falsifying relativity, Einstein would have been all over that to hop in and, and explain this as a relativistic effect. Well, he actually never addressed the Sagnac experiment or the Michelson-Gale-Pearson experiment. I think he went to the MGP construction site, shook the lads' hand, but never commented on it as like a relativistic effect or anything like that. Other people always provided that for them, and we'll get into that a little bit here in a second. But what we're looking at here is a paper in 1993 by Niklaus, who was doing an interferometer Sagnac setup. And they make note here that There's 22 explanations of people trying to provide a relativistic solution for the Sagnac effect with special relativity. And there's, and among them, there was one for general relativity, which we'll come to in a second. But here, this is just stacking up people trying to explain this phenomenon, right? Because maybe I'm wrong, right? Like I'm not, I didn't go to higher education. I don't know. Maybe I'm wrong. But all these people here are trying to explain it as a consequence of the postulates put forward earlier, and none of them successfully did so. And we'll take a look here. We'll go through the history of the.
Hold on.
Mm-hmm.
I gotta cut in. So the Sagnac effect is an effect which can somewhat famously be ascribed to a lot of different effects in different sort of frameworks of how you look at the question. Whenever you devise a particular internally consistent framework, you're going to be able to describe the Sagnac effect. That does not mean necessarily that the metaphysical interpretation of your description is going to be identical in every case.
Well,
I would, however, disagree. I forgot what I was disagreeing with.
Okay.
Hey, at least I'm honest.
No, you're good. You're good. Well, let's start with the physical fringe displacement, right? Let's forget about the theoretical. Let's talk about what's predicted. So in an inertial frame, those two lads in uniform motion would experience link contraction as a function of the square of their velocity, right? So a much, much smaller effect than what's physically measured. Would you agree?
No. I would agree that it's would I describe that as with the square? I know what you mean. We both understand the gamma factor. It's 1 over the square root of 1 minus v over c squared, the quantity squared. Yeah, so in that sense, but like I think if you actually do the expansion, I'm not sure what order it is off the top of my head.
I would highly encourage you to do the expansion and see what you get. Or
What will I get?
Not anything that produces a measurement that would explain the Sagnac effect, as we'll find, or as we'll find as we continue.
Where you actually don't need to do the expansion, because just doing it straightforwardly, entirely analytically, is computationally efficient. So.
Well, the theory predicts no fringe, though, like just as a baseline, right?
That's
and then
not true.
1 second, applying the link contraction time dilation, which would be, orders of magnitude smaller than what was measured, doesn't explain it at all. So it's not.
Which specific experiment are we talking about? Because I feel like you said multiple things that apply in different ways to different versions of this experiment. And the thing about the Sagnac effect is the base Sagnac effect on its own is somewhat difficult to characterize and to link specifically, without the context of other experiments, certainly, to a particular physical model. You need to have it in context with other experiments. For example, stellar aberration. Like stellar aberration is a and I'm sure you agree, a hugely important
very important. I'm so glad you mentioned it. Well, in the context of other experiments, which we're going to fully go over and cover, right? Because this isn't even this is just the surface of it. I can't wait till you see the rest of it. This is so awesome. But yeah, let's cover stellar ab real quick, right? So 1727, I think it was, or 2029, something like that. James Bradley had his telescope at his 90 degrees looking at stars. And what he found was that he had to tilt his telescope forward a little bit to keep the starlight in the center of the telescope. And what they found was over the course of a year, if you plot out that deviation from that perfect 90 degree zenny, it comes out to be like 20 arc seconds. And when they ratio that against the speed of light, it comes out to 30 kilometers a second. So they took that as proof that the Earth was in motion. And, it is a nice kinematic measurement, right? And it's certainly, that angle certainly does ratio to 30 kilometers a second. And if I were a heliocentrist, I would be personally ecstatic, because that's the only ratio they've ever got that gave them 30 kilometers a second. But I digress. So after that, though, Arago put a half-covered telescope, or I'm sorry, covered his telescope with a crystal prism. And the hypothesis was that to sort out the matter on if the Earth was in motion or if the sky was in motion, right? Because one of these implies that the Earth is stationary and the starlight already comes in at an angle, which requires the tilt, or the Earth is in motion and that's the cause of the starlight displacement. So we have two possible theories that angle produces. So to determine the which one of these hypotheses is valid, Arago took his telescope and half covered it with a crystal prism. And the idea is that when starlight intersected that centerpiece, he would either have to correct it more or not when it hit that refractive media, right? Because it's going to slow the light down, and then the velocity of the Earth is going to have to be compensated to keep it in the center. So he's going to have to tilt it a little further. He found that he didn't have to make that correction angle. And then a couple years later, Airy came along with what we're told is Airy's failure. But what he failed to detect was the velocity of the Earth. So the hypothesis again was that, to settle the matter of why the correction angle for the telescope is necessary. Actually, I have graphics for this. Give me 1 second. We can do the whole thing. Totally forgot about that. Are you going to
talk about the experiment where they put water in the telescope?
Yep, I'm doing that right now. I'm about to show some graphics for it too.
You see this? You see this, chat? This is, people who disagree working together.
Absolutely. Move this over here. All right. Okay. So we have, do you guys see that? Okay. Or did I share it on the good quality or the crappy one? Is it still 1080p, boys?
I see it.
Okay, cool.
It is, yeah. 1080, yep.
Cool, fantastic. All right. Okay, so let's see here. So to settle this matter, right, is the telescope in motion or is the sky in motion? We had two possible outcomes. And so Airy was going to put water in his telescope, and that was going to be the deciding factor. So if the Earth is in motion, when you add water to the telescope, it's going to slow the light down such that it's going to require you to make a further correction. And the predicted amount essentially was 1 arc second per kilometer for the velocity. So if the Earth is moving at 30 kilometers a second, then 6 months out of the year, you're going to have to tilt your telescope forward by 15 arc seconds. And then as it's going in the other direction around the sun, you have to tilt it back 15 arc seconds. That was the prediction, right? So 1 kilometer per, or 1 arc per kilometer, right? For over the course of a year. And what he found was he only had to correct his telescope by 0.8 arc seconds. So there was a slight correction, but not even close to 30 kilometers a second. And the logical implication here is that the Earth is stationary and the starlight already comes in at an angle. So this is, and this is viewed from the lens of, putting it on Professor Kinkerfuse's theory that, a stationary Earth with the Earth moving through it, and then any displacement, you would be able to attribute that to the velocity of the Earth. So that's why it's 15, right? So a stationary ether framework. Now, if the Earth is stationary and there's an ether wind, well, we actually predict there'll be a slight drift, and we could absorb that, no problem. It wouldn't be an issue if there was a medium between the light source and us, and that caused the drift. This would be something that's totally fine. But the problem here for the heliocentrist is that they need to attribute the full velocity to the Earth, right? Because that's what they were looking for, confirmation that they were moving with that first order measurement. All right. Let's see. So did I miss anything on that, sir?
If you do the calculation, and one of the effects, by the way, that you have to keep in mind here is the Fresnel drag of the water. Oh, sorry, you may not have mentioned. Did you mention the version of the experiment where they pour water into the telescope?
Explicitly.
Okay, yeah, that's what I thought. I just want to make sure. That when you actually do the calculation, I don't like which part of it is not consistent with special relativity.
So if special relativity were true and this water is carrying a velocity of 30 kilometers a second, it's going to require a correction. So real quick here, we have One second. Pulled it up and then I minimized it. So this is a note from Michelson in his 1887 paper on those results, right? Because you know how we were talking about the undulate or the wave theory and the corpuscle theory too. So this is also a pivotal situation here in regards to that, because he starts the paper off talking about Airy's experiment with the aberration being unchanged for the velocity when water was added. And he says he has a special note here, and then he says, it may be noticed that most writers admit the sufficiency of the explanation according to the emission theory, while it is in fact difficulty of greater according to the undulatory theory. So the wave theory and the emission theory. So the ballistic corpuscle light theory and the wave theory. For the emission theory, the aberration should be less. Hence, in order to reduce its true velocity, we must make the absurd hypothesis that the motion of the water in the telescope carries the ray in the opposite direction. So for the corpuscle lads, they had to say that the light accelerated when it hit the water instead of slowing down, and that's why it didn't correct. And then for the ether lads, they had to say that that there was, the stationary ether, mind you, right? But for some reason in the telescope, the ether is carrying the light in the opposite direction of the velocity, and that's why it's creating the illusion that it doesn't need corrected for. So that was where they were at in the 1800s with that. So I'm not really sure.
Fair point. I was unaware of this, so
yeah,
I will have to look at it and get back to you.
Yeah, dude, it's pretty intense. Like I had a back and forth with someone on Twitter about this, and
there's a lot of paragraphs here.
Yeah,
I'm not smart enough to just do a back and forth.
Oh no, you're good. I'm just giving you supplementary information to follow up on.
Yeah, no,
but
I'll check it out
this in conjunction with trying to explain this through the relativistic lens is like, it just leads to more problems. All right, so there's no velocity potential carried with this water apparently, opposite or width, and then so that's where we're at with Airy. So we can get back to what's it called? The interferometry stuff. Okay, so let's see the Sagnac effect. It's noted here that Paul Leveuve, that's not how you say his name, but anyways, I'll show you here in a minute. But anyway, this guy in 1917, so a couple years after the Sagnac effect, he shows up and he's like, boys, because the device is rotating, you can't apply special relativity to it. Rotation is an acceleration, and if things are accelerating, you got to apply general relativity to it. So he, using tensor calculus, right, it uses Einstein's new derivations for everything to conserve the rotation of the locally rotating Sagnac device into a gravitational field so that it can proportionally get that contraction stuff. But even that doesn't provide enough because the second, because it's second order effects, it's not going to be enough to be proportional to that, even though there's still, instead of denying the validity of the theory to apply to the frame, now they're like, okay, we'll apply the framework, but we're still in the situation where link contraction and time dilation predict too small of a displacement. So, and then of course you have the secondary issue. It's like, okay, well, suppose we have an inertial observer in the center of the device for the Lorentz symmetry, and then we have an observer at the rim of the device, which is in rotation. Well, we're in the same situation where they both don't predict a fringe shift pattern because they're both inertial observers. So, so they ended up scrapping that after a while, and we'll come back to the experimental falsification to that in 1942 with Dufour and Prunet. But that was put forward for a while to put it under the lens of tensor calculus and let the boys transform into it. Oh, Paul Levin, that's his name. Sorry about that. Okay, so now we have some issues here, right? So we've been talking about rotations and who applies to who, because some people nowadays say that, rotation of the apparatus means it's, special relativity doesn't apply, it's exempt, et cetera, et cetera. Well, there's something called Thomas precession, which we'll get to in a second. But before we get to that, to explain the effects of Thomas precession, which is basically they have an electron orbiting around the nucleus, and they say that, you know, because it's traveling at relativistic speeds, there's an anomaly with its magnetic moment or whatever, and it's like precessing a little bit. It's just causing a little wobble or whatever. That's kind of what they say with it. And then to explain that, this guy, Llewellyn Thomas, came along and he introduced a concept called a Lorentz boost, which I'll show the diagrams for that here in a second, but this is to give the history for what Post is putting forward. So anyway, this is under the confines of special relativity, explaining the anomalous electron situation as it has to do with the velocity, right? So it's within the mechanisms of special relativity, right? Velocity. So we're looking good so far. But then in comes your boy Post in 1967, and he's like, yo, check it out. I can explain the Sagnac effect, and I can explain Thomas precession. Here's how we're going to do it, boys. We're going to break electromagnetic processes down into their respective fields, the E and B, and then we're going to put those to a point called free space. Now, I know what you're thinking. There's not supposed to be an ether or an absolute frame that's preferred to be used, but we're dealing with rotation, boys, and times are desperate. So what we need to do is bind these fields to that free space and put it in rotation, and therefore the electromagnetic propagation will conform to the rotation of the fields with respect to that rotating fixed point. And it's like, dang, that sounds like a lot of craziness, man. How'd that work out? Well, a lot of people rejected it because it's not within the confines. It's not mechanistically the same as special relativity. So earlier, Tapioca was touching on the physical mechanism explanation versus the mathematic abstraction of it. Well, what this guy was putting forward, you know, nobody was trying to touch that because what he was doing was essentially using centrifugal acceleration or the centrifugal potential was what he was calling it. Like, so like he was taking that rotation and calling that centrifugal potential, and then using that to provide the contraction of the apparatus, essentially. And they were like, "Yo, dog, that's too close to general relativity, using gravitational fields for gravitational potential and stuff like that." So nobody really went with that. And then Ron Hatch ended up doing the math on this apparently, and this apparently does not predict Thomas precession. But I'm not versed enough in the math to break all that down. But it should be noted there was a big contention there from your boy Ron. And then let's see here. I think so. We're good on that. So back to actually, let me show you a Lorentz boost real quick. Okay. So the idea for the Lorentz boost is that the observer's in it's moving in radians relative to the center point. It's not the same. It's different. Well, what you do with a Lorentz boost is two Lorentz boost is equivalent to one Lorentz transformation. So what they're doing there is they're taking, when you're in rotation, you can have as many infinitesimal, you can break it up into any amount of infinitesimal points as you want for inertial frames. So if you do that and you do that twice, you'll have the equivalence of doing a linear Lorentz transformation. So what he's saying that to explain this rotational effect with an electron, suddenly special relativity applies to that within that framework when it doesn't have to explain a physical fringe or anything like that. Like they were content to apply special relativity to Thomas precession. Now, when you Lorentz boost and you apply that to Michelson-Morley, right, you don't get link contraction and time dilation in the same respect. So it doesn't explain that. So it's just like introducing a coordinate system rotation versus like a meaningful it's not meaningful in my worldview, but as opposed to the meaningful physical mechanism of link contraction and time dilation offered by the linear transformation. So it gets into conflicts with that. And then let's see. So Post was trying to, rectify all this and make everything cohesive. But again, it's like when you start going, oh, well, we can apply it to rotation here. Well, then it fails in other places and it's just not mechanistically cohesive. So, we're in, let's see, what year was that? 67. No answer from him in any meaningful way. Yes.
You covered a lot of topics since last time we spoke.
Mm-hmm.
Are you saying that Lorentz transformations or special relativity do not apply if you're in an accelerating frame?
So the argument that was made for Sagnac, and especially when I talk to people about it now, they're like physicists and whatnot, is the argument that they'll put forward is they'll say, well, the device is rotating, and rotation is an acceleration, and special relativity doesn't apply to accelerations. It only applies to uniform.
Oh, that's wrong.
Linear. Well,
They are
I mean,
wrong.
I completely agree. So these are the links I've had to go to.
You and I are in agreement on that. They're wrong.
Yeah, these are the links I had to go to figure out like who's right. So
no, it's actually a very common misconception that accelerations are not applicable in special relativity. So in special relativity, what is required is that, like, as I understand it, and like I could be wrong, okay? I'm not the world's authority on relativity theory by any means. But as I understand it, special relativity applies when the space, the physical space, X, Y, and Z, not time, not space-time, but when space is flat. Which means equivalently that any triangle that you draw between 3 points in that space will have an interior angle that sums up to 180 degrees. That's like one way of identifying if a space is flat. So you can absolutely have acceleration and you can treat it completely fine. You just do an integral in the context of special relativity, and you can do things both rotational and with linear acceleration, or a combination of the two. What you can't do,
dude, no way. That's awesome. No, I'm just blown away. I had no idea. Dude, these people were acting like that was just the craziest thing they'd ever heard of. You can't do it, blah, blah, blah. You're just like, nah, it's just an integral. Okay, dude. That's awesome.
I mean, to be fair, just an integral is if you don't have access to something that can approximate it by cutting it up into a whole bunch of really small, fairly easy arithmetic problems, which is just what numerical integration is. Very useful, very useful. But if you want to show a mathematical identity, it is only a guidepost. It's not going to get you to a proof, you know?
Yeah.
Numerical integration. But
Dude.
integration is fundamentally a very hard problem because you're trying to undo. You have to compute an antiderivative, and those aren't even always well defined. The function f of x equals x to the power of x does not have, as I understand it, a closed form antiderivative.
Dude, well, that's beyond me to know what you're talking about, but that is super interesting, and I will definitely have to come back and look into that because that's so funny, man. That they're just like, no, it's a different frame, can't do it, can't be applied. You don't know what you're talking about. That's awesome.
It's definitely like it's a thing that I have found in, and like you can tell a like competent, really like well-read resource like a textbook. Like some textbooks get this wrong. And the textbooks that like don't get it wrong point it out because they're like, yo, hold up. This is a thing that a lot of people misunderstand, even in physics. So yeah, anyway.
No, you're good, bro. It's awesome. All right, so let's see here. We got where were we at? I think this was, we'll just read here and see what we find. We imagine an infinite, oh yeah, so this is just Thomas precession. So we imagine an infinity of inertial systems moving uniformly relative to the laboratory system, one of which is instantaneously matches the velocity of the particle. The particle is thus instantaneously at rest in the inertial system and thus can be connected to the laboratory by Lorentz transformation. It is assumed that the Lorentz transformation will also be described with the properties, of the particle in the rest system as seen from the laboratory. Very nice. All right, so yeah, that was just further reiterating that despite the claims, you definitely can get rotation in there and acceleration. Very cool. And then, well, you know what's interesting? You mentioned the flat spacetime metric. They actually so you know in general relativity they have the curved spacetime metric and they have a flat one. Well, they'll actually use the flat one to derive that stuff as well. It's like they're already imposing it, you know. they're already going with general with special relativity, right? They already took it to an infinitesimally flat plane in general relativity. That's insane.
You are very often you are very often able to derive results from in the limit of small perturbations when you only have to consider the linear contribution, and then like look at that and compare it to observations, which is like what physics is about, and also look at and explore the internal consistency, which would be what mathematics is about, and that will reinforce and then often provide a pathway for a rigorous derivation that isn't based off of sort of mathematical intuitions. A lot of results are first derived from intuitions that aren't necessarily rigorously defined, but a lot of them are then later backed up with rigorous mathematics. The Dirac delta function is a great example. The best example in history would be calculus as a whole. I mean, calculus wasn't well founded rigorously until analysis was thoroughly developed in the 1800s. So,
shout out to the boys, Levi, Savita, and something Cabastro. Let's see. What, oh yeah, and that guy too. All the lads got together and calced out. Rock out with your calculator out, I think was the motto. All right, so we got the Sagnac derivation here. The displacement in time, or the change in time, the delta t is equal to 4a times omega over the speed of light. So this is just showing the length of the apparatus times the rotation, and over the speed of light is going to give you that angular displacement amount. And this is the classic derivation for it, right? So this is just a ratio of velocity over c to give you the predicted fringe amount. Now, in special relativity, if you took an apparatus that was 1 kilometer long and rotating at any velocity you want, you could never get it to produce, you could never get special relativity, length contraction, and time dilation to produce enough of that to cause the physical fringe that's measured by the rotation of the device. So the point made here was by A.G. Kelly, and he goes into the math over it. I just gave like the truncated version. But what he's saying here is that, due to the magnitude of the second order effects, you are never going to be able to mathematically facilitate that fringe pattern out of that theory, because it's a first order effect that's directly proportional to the velocity, whereas time dilation and length contraction are functions of the square of the velocity. Let's see. So surely a hero will emerge and explain the Sagnac effect as a consequence of special or general relativity. Did it ever happen, boys? Well, unfortunately, no. But we did have a quick introduction of the general theory to swoop it up for a little bit. So we're going to cover the brief history of general relativity in Sagnac. So the first introduction to what he calls curved linear, right? So straight, but also curved. And this is the idea that you're moving in a straight line, but reality around you is curved. So unless you could take the perspective of some like God frame, you would see from your reference frame, you would be moving in a straight line. But in reality, from that fourth dimensional perspective, you would be moving along the curvature of something, right? So, and this is where the term curved linear comes from, but, obviously a contradictory term, like relativity of simultaneity can't be simultaneous and relative at the same time. So they tried to, and this is a quick look at geodesic. Geodesics are very cool. This is one of my favorite parts of relativity. Whenever I look at relativity videos, I always look to see who has the coolest geodesic path in their thumbnails, and that will be the video that I watch. So this is just what I was talking about earlier. This is us looking at...
I want to reaffirm that and say that I completely agree with that metric.
Nice. So this is the what that curved linear path would look like from the God frame. So here we have a photon in a straight line, but Alan, it's going in a curve. Well, I know because we're in the God frame. But from old photon here, this would just be a straight line. And so this is what this is supposed to represent with curved linear and curved space-time and all that kind of stuff. So we're going to look at the Dufour and Prunet experiment now because, you know, an application of general relativity and acceleration in the rotating frame. So this curved linear situation is supposed to produce a result that explains the Sagnac effect. So in 1942 or thereabouts, some French lads, Dufour and Prunet, got together with a specially configured Sagnac apparatus where the top half is stationary and the bottom half rotates. And it's separated by, 5 centimeters, I think it was, and then 45-degree angled mirrors. So what it's doing is they have a source on the lab wall and a detector on the lab wall, and they also have a detector on the rim of the rotating device. And what they're doing here is they're testing to see if the fringe shift pattern will be translated to the inertial observer on the wall, right? Because there's some contention here that, well, the device is rotating, so it's a non-inertial frame. And of course, what determines the inertiality of a frame, you could say, so with the recorder being on the rotating apparatus, they say, oh, that's a non-inertial frame, so blah, 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 even though Tapioca already went over, you know, there's ways you could definitely fit relativity theory in there through the special theory. Give me 1 second. Let me get the streams going. They're restarting.
You gave me like 2 more minutes. I was going to be able to completely shut this thing down. I was trying to sabotage you so hard.
Nice. Nice.
Yeah, we just learned that Tapioca here is actually the grandson of Van de Graaff.
Yeah, dude. Shout out to your boy Vandy.
Yeah, no, I've known Alan longer than I think any of y'all.
Really?
Yeah, we met through Pitch Lumen.
Yep. Old Pitch.
Oh, okay. So are you here because you knew he was going to be here, or you just happened to be here?
I just happen to be here. This is one. So I keep this particular channel actually. Currently, it's number 3 on my sidebar. But like everything that's in the top 10, I basically gets equal eyesight from me because I like coming here every so often.
Nice.
So how long have you been a flat earther?
I'm not a flat earther, man.
How long before you become a flat earther?
I like that question.
If I absorb the what's it called? Nah, never mind. We'll not get into that. Anyway, whenever you guys are ready to continue, my stream's on. My stream's good to go. So if we can jump back into it, I can finish this bad boy off. If you guys are still down.
Nah, we're over it.
All right.
Yeah, I reshared it. Yeah, good to go.
All right, cool. All right, so to pick up where we left off, we were talking about general relativity and its application for the Sagnac effect. And then we were looking at an experiment that was done where an observer was fixed to the lab wall, and also there was an observer at the rim of the rotating device. And what they found was that the fringe was measured by the observer fixed to the lab wall. So there's some mechanism, right, that's causing the path length to be fully, or when the path length is increased due to the rotation of the bottom half of the interferometer, there's some preserving aspect of absolute space that's making that inertial lad on the fixed to the lab wall make that measurement to keep that consistent with the velocity of the rotating apparatus. So here's some cross sections of what the light paths would look like with the 45-degree angle. So you guys get a nice visual of that. We got your centerpiece of the axis of rotation, and then the 45-degree angled mirrors to facilitate that up and down translation there. And then here's the worst picture ever taken of the apparatus. And so that's what we're looking at here. Bottom half rotate, top half stationary. Yeah, it's not great, but somewhere in here is a lad fixed to the lab wall, presumably.
Yo, I gotta say, I'm looking at this thing. All I see is 3 ghosts that look like they're out.
Yes.
Am I wrong?
No, that's the original Sagnac apparatus is actually 3 ghosts. So you're dead on. So the measurements that were shown from this configuration, the classical theory predicts for a fringe displacement of 0.53 fringes, or 0.053 fringes, and the relativistic theory predicts 0.05 fringes in the configuration with the lab wall observer versus the what do you call it?
Ghost potato observer?
Yeah, versus the ghost potato observer on the rotating device. So for those of you who aren't familiar, but this is an incorrect prediction, right? The inertial observer should always be measuring CSC. There should be no reason that the translational speed was preserved through a measurement of absolute space. That's not supposed to happen in relativity theory. So this prediction is way off here by a factor of 10. And Paul Levov's explanation was, hey man, because general relativity is a theory of gravitation and this device is in rotation, there's going to be that inward attractiveness. This is his like rationale for it. Therefore, we have to use the center of the device as the preferred frame for the calculation to be done. Because if you invoke the center of the frame, you can, quote unquote, make the same prediction there. But even though they, even though they don't do that, I'm sorry, they can't do that because, then they're invoking a preferred frame, right? They're invoking a stationary frame to make the correct prediction when the general theory is about general covariance. And this explicitly, should be covered in its, it should definitely be able to make this prediction as is if it's going to follow a general covariance, meaning that it doesn't matter if the frame is accelerating or not, it should still make the correct prediction. And let's see here, unlike what we're kind of half told about special relativity only being applicable to certain types of motion. And then
I will take credit for the other half of that half told.
Nice. Absolutely. And yeah, you single-handedly pretty much, you and our boys Solzy, who put together that math for the different types of motion all being the same. So shout out to that.